Welcome back. In the last video, we gave a little bit of an overview of the file structure that we'd like so that we can deploy our Food Vision Mini app to Hugging Face spaces. Now, you might have the question, I've kind of just thrown this at you, but you might have the question, why use this structure? Well, there's no reason other than because it's one of the simplest we could start with. Now, of course, as your demos and your apps and your models get more complicated, you could complicate this as much as you want or make it more sophisticated. But for now, we're just going to keep it simple so that we can experiment. And if something doesn't work, well, we can update it over time. So let's now, 8.3, we want to create a demos folder to store our Food Vision Mini app files. So this is our demos directory and then Food Vision Mini. So let's start doing that. Let's go import shutil and then from pathlib import path. Now if you want to look up what shutil is, you can go python shutil. What do we have? High level file operations. There we go. Directory and file operations. So that's what we do. shutil allows us to do directory and file operations with Python. So we can manipulate directories and manipulate files using Python. So I'm going to get out of a couple of these. Got a fair bit going on, but that's all right. We got this. So let's create a Food Vision Mini demo path. So I want to call mine Food Vision Mini demo path. Wonderful. And then I'm going to set this to demos, Food Vision Mini, and then let's go remove files that might already exist and create a new directory. So this is just in case we already had a file called this. We don't want, if we're moving forward and creating this file structure, if it already exists, we kind of want to remove it and then recreate it. So if it exists, let's remove it. If not, we're going to create it anyway. So if Food Vision Mini demo path dot exists, so this is a path method that's just going to check if it exists. And if it exists, I want to use shutil remove tree or rmtree for, that's going to remove the file tree that is present at this path. Now, as I said, if it already exists once we get to this cell, we want to delete everything, but then we want to recreate it so that we start from afresh. This is like saying, hey, if something exists, delete it, and let's start from fresh every time we run this cell. Make dir, so now I want to make the directory. I'm going to set parents equal true, exist okay equals true, and then else, if it doesn't exist, so this is else, if it doesn't exist, we're just going to run this exact same line as well. Beautiful. There might be a better way of doing that, and if in fact, if you think of one, please let me know in the GitHub discussions so that other people can see as well. Food Vision Mini. Let's have a look. What files do we have in there? None, which is exactly what we thought we should have. So we have demos, Food Vision Mini. Wonderful. The first piece of our puzzle is together. We've got this. Now, you might have already tried this. My challenge to you is to fill it up. We've got this folder. Fill it up with these files here. app.py is going to be accumulation of our Gradio interface and everything that is required to run that. So give that a shot, and over the next few videos, let's start to fill up our Food Vision Mini demo directory. I'll see you there. Welcome back. In the last video, we created our Food Vision Mini demo folder. And what we're moving towards doing is filling it up with all of the requirements for our deployed app. So all of these things here. Now, how about we start with creating some examples? Because that's what a demo is all about, right? Demonstrating something. And a demo is not really a demo without any examples of how it works. So let's create a folder of example images to use with our Food Vision Mini demo. So what we want, how about we just get 3 images in an examples directory, and the images should be from the test set. So how about we copy some files from the test directory here, some of these images, and we put them into Food Vision Mini under an examples directory. So what we're going to have to start with first is we're going to create that examples directory. So import shutil, because we're going to use that to copy. Remember, shutil is from Python, shutil Python, high-level file operations, directory and file operations. So if we want to move some images from one file to another, we can use shutil. So from pathlib, import path, and let's go create an examples directory. The reason we could do all this manually, right? We could create a file manually, move some files, but I like to do things with code. So if we were to revisit this notebook and rerun it again from the top, it would recreate all of these files for us. Sorry, I want to call this examples. And now I want to set up Food Vision Mini examples path. I'm going to run mkdir for make directory. Parents equals true. It's going to make the parent directories if they don't exist. Exist okay. If it exists, we don't want it to error out. So let's see what happens here. We've got Food Vision Mini, and we've got an empty examples directory now. So what we want to do is copy some images from pizza, steak, sushi 20% test. Some of the images, maybe one pizza, one steak, one sushi, just like we've got here in our app. So we can click on an image and there we go, sushi. Good demonstration there. So how might we do that? Well, we could just randomly copy one of these paths and then go pizza path equals that. But like all good machine learning cooking shows, I've got a couple of images I prepared earlier. So let's just go into here and do our little trick. I'm going to copy this section here. This is from 8.4, creating a folder of example images to use with our Food Vision Mini demo. So this is just 3 paths to 3 images I've picked manually, one from sushi, steak, and pizza. Of course, we could do that randomly, but these ones are visually appealing, so that's why I chose them. So random test data set image paths. They're not actually random because I've chosen them myself, but that'll do for us. 3 images, beautiful. Now, here's where we can copy the 3 images to the examples directory. So this is where shutil is going to come in. So for example, because this is a list, so for example, in Food Vision Mini examples, what do we want? Let's set up a destination. So the destination file equals Food Vision Mini examples path / example.name. So I just want to print this out and show you what it looks like. Destination. Food Vision Mini examples. Oh, I forgot Mini. There we go. So this is the destination. Demos, our demos folder, Food Vision Mini examples. And now the name comes from here. So that's example.name. So let me just print out this, print example.name. There we go. So the .name attribute is just getting the name of the target file from the path. Isn't path manipulation beautiful in Python? Now let's go here. I'm going to print out a little info tag. Info, copying, example to destination. Now we're copying them because we want them to remain in our test data file. We don't want to move them, we just want to copy them. So that's why we're using copy. Now let's actually do it. shutil, copy to, and then we're going to go source equals example, and dst, which stands for destination, is going to be our destination. So let me just get rid of this. Now, of course, where can you find out what that is? Well, if you go to shutil and you look up what copy to does, oh, typo, copy to, there we go. Identical to copy, except that copy to also attempts to preserve file metadata. So copy to is a little bit more comprehensive, or tries to be more comprehensive than copy. So if any file metadata is associated with our file, it tries to copy that across. Not necessarily important for our use case, but I just like to use copy to, just in case there's some important information tied to a file that we would like to preserve. So let's run this and see if it works. Oh, look at that. I love these info messages. So copying data, pizza, steak, sushi, 20% test, sushi. 2 demos, Food Vision Mini examples. And there we go. Let's go into here. There's some of our test images. It's going to be one of those images. Look at that. Wonderful. So there's our example file for pizza. And there's our example file for steak. And there's our example file for sushi. Now, of course, you can customize those, change them how you want, but I'm going to leave it like that. So now we've ticked another box in our file layout. So which one should we do next? How about we move the model? But actually, I just realized our examples file is not going to do well unless it's in the format that Gradio takes. And what format does Gradio take? It takes a list of lists. So let's now verify. And what I mean by that is our Gradio demo. If we come back, Gradio demo, the examples list is in a form of list of lists. So I'll just show you this. Example list. Verify that we can get a list of lists from our examples directory. So how could we get all of the file paths here into a list of lists like this? Well, let's give it a shot, hey? I think we can do it with OS. So get example file paths in a list of lists. So we've got a file path to our Food Vision Mini examples. So let's go example list equals bracket bracket. Now we need to pass in the examples directory. Why do we need to do this? Because our app.py is going to be referencing this directory. So app.py is in the Food Vision Mini level, whereas examples.py, the examples are one directory deeper. So that's why we have to append that or prepend that examples directory to the start. Now let's keep going. This will make a lot more sense once we actually create the list. So plus example for example in os.list the contents, so list the contents of this given directory. Food Vision Mini examples path. Let's see what this looks like. Oh, wonderful. There we go. Okay, so now we have a list of lists containing our example files. So this is examples. See how we're slowly building out this directory structure? Wonderful. So next we want to move over our model. So you might want to give that a shot. You can use shutil and move it, or you could even use just the move command. So mv. So give that a shot, and I'll see you in the next video. Welcome back. Now we're slowly building out the functionality of our Food Vision Mini demo. In the last video, we created this examples directory with example images. Now let's get our model in there. So let's write moving our trained FNet B2 model to our Food Vision Mini demo directory. You might have already given this a go, and if you have, I applaud you. But let's now do it together. So what I might do for this one is import shutil, and I'm going to create a source path for our target model. Now we can get this source path from back up here where we saved our FNet B2 model. So where was that? Saving it here. So this is our best performing model in terms of our criteria. So good test performance, but as well faster latency than our feature extractor on the CPU. So I'm going to create a file path here, FNet B2 Food Vision Mini model path. Bit of a mouthful, that name, but there we go. Okay, now let's create a destination path for it. Create a destination path. Where do we want to move it for our target model? So we want to move our FNet B2 Food Vision Mini model destination. what should our model destination be? We want to move it into this directory here. So let's set that equal to Food Vision Mini demo path / which is this file here. That's the demo path / fnet b2 Food Vision Mini model path. And we're going to split that on this and get that. Let's see what this looks like, hey? Wonderful. Now, why do we split this? So let's just see what this looks like. So truly, we didn't even have to do that. And if we get this, so all we're doing with that line is removing models /. So this is where it currently lives, and this is where we'd like it to live. So this is where we'd like our model to move to. So that's why we've created this path here. Again, we're trying to do things as much as possible with code rather than just hard copying things. So let's try to move the model file. And if we can move it, we want to move it. But if it has already been moved, we want to say, hey, it's already been moved. So let's go here, try, and then we're going to print a little info string and go attempting to move fnet b2 Food Vision Mini model path. And then we want to move it to the destination. So I'm just going to copy in this destination here. Wonderful. And then if we can move it, we want to move it. So move the model, shutil.move. We need a source. So where are we trying to move something from? So it's this path here. We want to move it from this source to this destination, which is our destination path, which is, of course, what does that look like? There we go. Demos, Food Vision Mini, that's our model path. So that's what we're trying to do. Now, if we succeed in doing that, let's print out an info tag. Info model move complete. Now, of course, we could, as I said, we could just drag and drop our model file. Models, we could just drag that into there. But I want to do this all with code so that we could run the whole notebook again and it all works. So if the model has already been moved, check if it exists. So let's go accept and then print info tag. I need to make a shortcut on my keyboard for the info tag. No model found at fnet b2. So this is the source. So if it's been moved from the source, we want to just print out this message. If there's no model found at the source, perhaps it's already been moved. And then the next line, we want to check if it exists. So model exists at, and then the destination, we want to check, does it exist at the destination? Oh, excuse me. I just want to get this. Model exists at the destination. And then we can pass that in, .exists. Wonderful. So you ready? A whole bunch of try and accept code, but once we step through it, it makes a bit of sense. So it makes sense to me. So we have a source path for the model and a destination path. And we want to try and move the model using shutil, move from the source to the destination. And if the model gets moved, we say model move complete. But if there's no model found at the source, we want to then later check and say, hey, maybe it's already been moved. And then if there's still no model found at the source, we want to say, does it exist at where we're trying to move it to? And if it does, we want to print out true or false. So let's see this in action in 3, 2, 1. Oh, we might see this model disappear into here. That's our ideal workflow. Oh, this hasn't refreshed yet. Let's refresh. What happens? There we go. It moved up into there. So we did that. Now, if we run this again, it's not going to do anything. It's going to say, attempting to move model this, no model found there, model exists at this file path, demos, Food Vision Mini, pre-trained model, yep, PTH, true, wonderful. Okay, so now we could replicate this move with code if we came back to this notebook later on. So we are one by one filling out this Food Vision Mini demo. So what should we do next? Well, we just moved our trained model state dictionary file. How about we create model.py? Now, model.py is going to need to have the functionality of our FNetB2 model function, or create FNetB2 model. So you might want to give that a shot. Save this code functionality into a Python script called model.py inside Food Vision Mini. Now, if you'd like some help with that, you might want to refer to PyTorch Going Modular on how you can save a code cell to a file. So give that a shot, and then in the next video, let's create model.py to load and create an instance for our FNetB2 model. I'll see you there. Welcome back. In the last video, we wrote code to programmatically move our trained FNetB2 model to our Food Vision Mini directory, and we're slowly filling out this demo app for functionality. We now need to create a model Python script to load in this state dictionary. So how do we do that? Well, let's find out. And you might have already done this because I issued the challenge in the last video. So congratulations if you got it working, but let's now do it together, hey? Into a Python script. And I'm going to call this model.py for simplicity and say we have a saved.pth model state dict and want to load it into a model instance. Let's move our create FNetB2 model function to a script so we can reuse it. Wonderful. So our create, this is actually going to be pretty quick because we've got the functionality ready to go. So this is one of the reasons we turn this into a function. So I'm going to copy this and come back down to here, and then I'm going to write it there. And so there we go. We're done. No, I'm kidding. Let's write this to a file. So how do we write it to a file? Well, we can go write file, which is a magic for Jupyter and Google Colab notebooks. And then this is going to write the contents of this cell to demos/foodvisionmini/model.py. However, what we have to do here is, because it's going to write it as a Python script, we need to import the dependencies that we need for this file. So we need Torch, and then we also need Torch Vision. And then what else does this use? We also need NN. So let's go here, from Torch import NN. And let's run this. Beautiful, look at that. Demos Food Vision Mini model.py. Do we have it over here? There we go, model.py. Wonderful. So now we can write something like from demos.foodvisionmini import model, and then we go FNetB2 model, and then FNetB2 transforms import equals, I'm doing this so I save it to different variable names, equals model.create FNetB2 model. Let's see if this works. FNetB2 model. Boom, there we go. So it works. So now we can reference this model.py script in our app.py script, which is in fact the next step we're going to work on. So we've got tick, we've got tick, we've got tick. Now we need to create app.py. Now this is probably going to be the largest file that's within this, but it's not going to contain anything too drastic. In fact, app.py, all it needs to contain is our Gradio app. So I'm giving you this as a hint so you can try it out. A way to get our example list, and a prediction function, and then just some code up the top to import our FNetB2 model from model.py. I think that's all we need. So give that a shot, creating app.py. For a little spoiler, you can go to here, Food Vision Mini, files and versions, and then there's app.py. That's a bit of a reference. But we're going to create that together in the next video. So I'll see you there. Welcome back. In the last video, we created Food Vision Mini model.py, and this is what's going to define our model instance, our FNetB2 feature extractor, because in the previous video, we moved our save model file there. So now let's create app.py, which is going to be the brains of our application, and it's going to be the default application that Hugging Face Spaces tries to run to create this demo. So you might have already given this a shot, but let's now do it together. 8.7, this is so exciting. We are creating our Food Vision Mini app as a deployable app, not just a demo in a notebook, a deployable app. Our Food Vision Mini Gradio app into a Python script. And now, truly, this app.py is not going to have anything revolutionary. We've already done the major steps. So let's break it down. It's going to have 4 major parts. The app.py file will have 4 major parts, and this is just tying everything together. So number 1 will be imports and class names setup. So we need to import some basic functionality, our dependencies for our app, as well as set up the class names. Now, again, class names we've already got in a variable. We just have to make sure we put that into an app.py so it can be referenced. Number 2 is going to be model and transforms preparation. So this is just going to be utilizing this function here. So our model is going to load in using create FNetB2 model, our FNetB2 feature extractor instance will be created by that, and the transforms. We're going to load our model in by loading in this saved state dict over here. Then number 3 is we need a predict function. So this is predict from above. Now truly this could be any function. We've just called ours predict, but that's the Gradio. This is our interface. If we look into the documentation interface, this is just our function. So a callable function. And you can really put this as almost anything you want. We've just called it predict because we're going to pass our Gradio interface an image, and we want some outputs in the form of a label, which is what our predict function does. It maps our inputs to our outputs. So that's going to be number 3, and we've done that just up here. So we want this function, predict, pass it an image, get back a dictionary and a prediction time. And then finally, number 4, what do we need? Well, we need the actual Gradio app. So Gradio app. This is going to be our Gradio interface plus launch command. Because after all, once we finish writing app.py and upload that to a Hugging Face space, Hugging Face is going to try and run that app.py, and the launch command is going to launch this app. So let's see this in practice, hey? I'm going to start off by writing the file. I like to live dangerously here. Let's, whatever we write in this cell is going to be written to file. So Food Vision, better make sure the file path is correct, eh? Food Vision Mini, app.py, beautiful. And so we want to write it into here. What do we need? Imports and class name setup. Well, you might not know, here's the thing, you might not, and in fact, I'm going to comment this out so I get the Python formatting to begin with. 1 is imports and class names setup. So here's a little tidbit, is that I sometimes and quite often miss out on different imports because I forget what my code needs. So sometimes the only real way you can know the imports that you actually need is to try and run your app. And if it doesn't run, well, then you're probably missing an import. But I only know these ahead of time because, again, this is a machine learning cooking show. I've cooked these dishes up well ahead of time. So from model import, this is one that you might forget. So from model import, the reason we're importing from model is because app.py is going to live inside Food Vision Mini. And so from model import create FNetB2 model is importing from model.py. So that's a little hard to know ahead of time. I only learned that through trial and error. So don't worry too much if you make mistakes here. It's all about experimentation. So we're going to import the timer so we can time, and then from typing, I'm going to import tuple and dictionary. Wonderful. And then I'm going to start by setting up the class names, and that'll be section 1. How good is that? So I'm just going to do it nice and simply. I'm going to hard code it as a list. We could, if we had more classes, maybe we would save them to a file and import them. And in fact, no spoilers, but we might do that later on when we build a bigger demo. But let's now move on to section 2, and that is model and transforms preparation. So here's where we're going to leverage our create fnet-b2 model function from model.py. Remember, this app.py script is being written in the context of the Food Vision Mini directory, not any other directory from inside this directory. That's demos, Food Vision Mini, app.py. It's not there yet, but it will be. So let's go model and transforms preparation. And we'll go fnet-b2 and fnet-b2 transforms, just in the same style that we've been using. We'll go create fnet-b2 model, and then we'll set num classes equals 3. We don't have to, because that's going to be the default. If we look at model.py, num classes equals 3 is the default, but we'll just do it anyway. We could also use something like this, because we've hard-coded our number of classes, or our class names, length class names. There we go. But I'm just going to put as 3. Beautiful. Now, what's next? Well, we need to load the saved weights. So this is going to be, again, within the context of this directory. This is our weights path, our state dict. So that's the file that we want to load in. How can we do that? Well, let's see. We want to go fnet-b2, which is the model that we just created above. Then we want to go load state dict, and then we want to pass in torch.load, and then we pass in the file path with f to this. However, if I copy this path, I'm going to put it in here, we get it within the context of Google Colab. So I actually want to delete all of this and only pass it in within the context of the Food Mini directory, because app.py is again going to live within this directory, so we can just straight away call this file path there. Again, I only know that ahead of time because I've been burned a few times. And then this is another one that we haven't worked with before, but we want our model to run on the CPU. So a little tidbit is that if we saved our model state dictionary after training on the GPU, it might by default think that we want to load it back onto the GPU. So this is where we hard code it to go, hey, you know what? When you load in this state dictionary, load it to the CPU. So load the model to the CPU. Again, if you don't do that, you might get some errors if you don't have access to a GPU where you deploy your Gradio application. So let's go to step number 3. What are we up to? Predict function. Oh, this one's a breeze. We've already got this ready. So predict function. Let's go, $, because once we deploy Food Vision Mini, we can sell it and ride the money straight to the top. Well, maybe we have to make it a bit better. We're going to find our predict function. Here we go. This is what we want. We can almost copy this directly into the app. And in fact, we're going to find out later if we can't and we have to update it. But let's just copy that in there. We've already done that. We've already imported that. So do we have everything? Timer, yes we do. fnet-b2 transforms, yes we do. fnet-b2 eval, yes we do. Predprobs, timer, I think that's it. Predict function, done. So this is just mapping again our inputs, which is an image, to our outputs, which is a prediction dictionary and the number of time, or the time that it took, so that we can get this rich output over here, so that we have something nice and pretty with stake and the prediction probabilities and how long it took. We've got one more step to do, and we've almost done this step as well. So let's come up here. we need step 4. We'll come down. This is step number 4. We have our Gradio app. So let me write this down. We want Gradio app. Now there's one thing missing from this. So this is just the exact same app that we want to run as before. But what are we missing? In the context of just this app.py script, it might not be immediately obvious. But if we want our example list to load, well, we need to load in those examples from this example directory rather than just the example list variable that we have. Oh, example lost. Yeah, they are definitely lost because we don't have access to them in app.py. We need to create this in this app demo. So, or app.py file. So let's go here, create example list. And how can we do that? Well, another thing that we've prepared earlier. We've already got it here. Example list equals examples plus example, for example, in OS list directory. This is the one thing that we won't have in app.py. We'll bring it down here, create example list. Oh, example list. What don't we have? We don't have access to this. So what can we change it to? Well, it's just going to be examples. So if OS lister is going to list the context of examples, this is going to be this examples directory because app.py is going to live in the context of Food Vision Mini. So there we go. I believe we've got everything we need for app.py. And of course, we're going to find out if we don't. There we go. We're going to find out if we don't when we try to deploy it, and then we can fix it on the fly. So app.py. There we go. So we've got our beautiful Gradio demo that we can upload to Hugging Face Spaces in 72 lines of code. And truly, we could reduce this if we wanted to. We're being a bit verbose, but that's on purpose. So what do we have left? Let's go back up to our little file structure tree. We've done model.py, done examples, done app.py, done saved model. We just need requirements.txt. Now, what is this going to be? Well, when Hugging Face Spaces tries to deploy our app, it's going to try and import a few things, but it won't necessarily have those dependencies such as Torch installed. So requirements.txt is going to tell Hugging Face what dependencies to install when we try to deploy our app. So you might want to go ahead and give it a shot of creating requirements.txt. We're going to need 3 things. So I'm going to write down here. What are we up to? 8.7? 8.8. Creating requirements.txt. We need 3 major things. That is Torch, Torch Vision, and Gradio. So give that a shot. If you want to look up how to create a requirements.txt file, how can you do that? Well, you can search create with Python. A whole bunch of great resources there. So give that a shot, and I'll see you in the next video. We'll create the final piece of our puzzle for our Food Vision Mini demo app. I'll see you there. Welcome back. We have got one more step left to go to complete the creation of our Food Vision Mini demo directory, and that is with a requirements.txt file. You may have already created this. Last video, we ended with a challenge of creating it, so I'm just going to fill this out a little bit. Creating a requirements file for Food Vision Mini, and it's going to be called requirements.txt, and let's just write down here, the requirements file will tell our Hugging Face space what software dependencies our app requires. So we need Torch. Let's write down here. The 3 main ones are Torch, Torch Vision for our pre-trained models and transforms, and Gradio, of course, for our demo app. So let's just make this straight off the bat. Write file, demos/Food Vision Mini. Now, I'm going to be specific here with the versions. We don't necessarily need to explicitly say the versions of each software package that we need. But if we don't, and some updates happen to Torch, Torch Vision, or Gradio in the future from the versions that we're currently using, our app may error. And I believe this needs a capital M. So let's just check what Torch version we're using. Version, and then Torch Vision, torchvision.version, and then Gradio or gr.version. Wonderful. So these are going to be the minimum versions for our app so that it works. So we want to install Torch 1.12.0. We could do 1.12.1, but I'm going to stick with 0.0. And then we're going to go Torch Vision 0.13.0. If you're watching this video way in the future, there may be Torch version 1. A higher number here, and a higher number here, and a higher number here. Don't worry too much. If there's any breaking changes, just let me know in the GitHub under discussions or issues, and I'll fix it up. But for now, we're going to stick with these versions, and then we'll go Gradio equals 3.1.4. Because when I first made this, Gradio's pretty fast. They release some updates pretty quickly. We're not missing out on too much functionality for using 3.1.4. I just know that our demo works using that version. So let's go there. Boom, look at that. I think we have everything we need. Look at that, that's a beautiful little app. So we could download that and upload that straight to Hugging Face Spaces. In fact, you might want to give that a go. New space, you can give it a name, a license, Gradio, etc., etc. We're going to do that in the next section. But for now, let me just get rid of those. We have got our Food Vision Mini demo outline. So we'll come back up here. Have we satisfied everything? Pre-trained model, yes. App.py, yes. Model.py, yes. Examples, yes, yes, yes. And requirements.txt, yes, yes, yes. Wonderful. I think there is but one, which is actually a few steps involved to upload all of these files to Hugging Face Spaces. In fact, you might want to give that a go. If we go to PyTorch model deployment, if you want to skip ahead, you can go to section number 9. There are two main options for uploading to a Hugging Face space. Uploading via the web interface, there's the documentation for that, or uploading via the command line or terminal. So check out those resources and give it a shot. Otherwise, in the next section, section 9, we're going to deploy our Food Vision mini app to Hugging Face Spaces. So I'll see you there. Welcome back. In the last video, we finalized the last file that we needed, requirements.txt, for our Food Vision mini app. So now we're up to section number 9, and by the end of this section, we'll have deployed our Food Vision mini app to Hugging Face Spaces, and we can share it to our friends all over the world. How cool is that? So if they're eating pizza, steak, or sushi, they can take a photo of it and have our app classify it at a pretty decent performance level. Hugging Face Spaces. So of course, we want to somehow get these files onto Hugging Face. And like I've got them here, this is again a machine learning cooking show. I prepared these earlier. So how can we do that? Well, we kind of touched upon in section number 9 of PyTorch model deployment. There are two main options for uploading to a Hugging Face space, also called a Hugging Face repository. And that is you can upload through the web interface. So like in a drag and drop sort of format. We'll have a look at this in a second. Uploading a file. And then the other way is adding files to our repository through terminal. So you can do this from the command line. This is what we're going to be focused on. Again, if you need some help in understanding what's going on with Git and GitHub, I'd highly recommend Git and GitHub Free Code Camp, tutorial for that. There we go, crash course, heaps of resources there. But let's keep moving forward. And then actually there's one more bonus way. There's a Hugging Face Hub Python library, which you can use. So this is going to help you upload things to the Hugging Face Hub. And now the hub is kind of a catch-all term for models, data sets, spaces, everything you can imagine. So I'll leave that as extracurriculum. We're going to focus on one way in particular. So I'll get out of there. That is uploading via the command line or terminal. And remember, if you get stuck, all of the steps that we're going to be going through are available here. So the first thing we want to do is, if we're working with Google Colab, is we want to download our Food Vision Mini app files. Now, if you're running this locally, the steps might be quite a little bit different, but we just want this Food Vision Mini file, we want it available on our local machine so that we can upload it to Hugging Face. So let's see how we can do that. First of all, I'm going to go ls demos. I might just put in here text. I want 9.1 and downloading our Food Vision Mini app files. And I want to put here, we want to download our Food Vision Mini demo app so we can upload it to Hugging Face Spaces and have it deployed. And I just want to put a little note here in the videos. Of course, this is in the reference material, but just to make it clear, I'm going to copy this into there. So that way you can reference this later if you want. You want boom, boom, and boom. So let's push forward. Let's see what's in the context of our demos Food Vision Mini. Wonderful. Oh, we've got PyTorch as well. We'll probably add that to a git ignore folder, but I think that might be there by default. So this is just saying, hey, this is the folder. We've got our pre-trained model. We've got app.py. Yep. We've got model.py, requirements.txt, and then our examples directory. It doesn't list what's in there. I wonder if we go ls.la, will it list everything? No, it doesn't. That's all right. We could just list what's in examples like that. Beautiful. So now what we want to do is download the contents of this. Now we could do something like this on Google Colab. Oh, we can't download it. We could download it file by file. Download. Might be waiting a little while for that. But let's zip together Food Vision Mini and all of its contents so that we can download it as a single file. And the way that we can do that is by, first and foremost, we're going to change into the Food Vision Mini directory and then zip it from the inside. This is so that we can download it as a zip folder. And a zip folder, what is a zip folder? It's a compressed version of a directory. Compressed zip folders overview. Folders that are compressed using the compressed zip folders feature use less drive space and can be transferred to other computers more quickly. So it's just basically, we're going to combine or zip together every folder or every file and folder, because there's an examples folder, in Food Vision Mini into one file. We'll see what this looks like in a second. So I'm going to change directory, cd demos Food Vision Mini, and then I'm going to run at the same time the zip command, and I'm going to call R for recursive, which means every file within recursively zip. I'm going to, my target directory to zip to is foodvisionmini.zip, and I want to zip everything from within. So let me just step through this. Change directories into, because if we go, what's the working directory? Print working directory. Content. We're here, but we want to change into here. And then once we're in there, let's zip recursively everything into a file called foodvisionmini.zip. So that should end up with demos, Food Vision Mini as a directory. And then we should end up with foodvisionmini.zip here. And the star is saying zip everything that's within the current directory to this. A lot going on, but if you want to look it up, you can go to zip command Linux. So these are very helpful to learn because a lot of computers worldwide, including Google Colab, runs on a Linux backend. Yeah, zip command in Linux with examples, how to zip files and directories in Linux, a whole bunch of examples there, but that's essentially what we're doing. And we're going to add one little tag here, and that's X for exclude. That means, oh, see, that took a little while to download, but now we've got our trained PyTorch model. We don't want that. We want everything in one file. exclude, or the X stands for exclude. So we want to zip everything except for anything ending in PYC. And we also want to exclude anything ending in IPyNB, which will include IPython checkpoints or Jupyter Notebook checkpoints. Remember, Colab is IPyNB, so we don't want to include any of those. We also want to exclude anything to do with PyCache. We don't need that. These are just files that we don't need. You'll see these quite often ignored. IPyNB checkpoints. And we'll put a star there. So let's see how this goes. Or maybe, do we need to do? Yeah, let's just see how that goes. There we go. Did it add that? Oh no, we need to add a zip there. A star on the end there. Beautiful, there we go. Okay, so what do we have over here? foodvisionmini.zip, wonderful. So of course we can download this like that. It's going to start to download, but we can also do this programmatically. So now we've combined everything in Food Vision Mini, as you can see, app.py, examples, that first image, that second image, model.py, requirements.txt. We've got that in our zip file now. But, we could download it here manually with buttons, but as I said, we want to try and do as much as possible programmatically. So download, if you're working locally, this might be a little different. So you might have to download it manually, but if we're working on Google Colab, which is what we're doing now, we can go from google.colab, import files, and then if we can get files, we want to files.download. Let's download demos/foodvisionmini.zip, and then accept. We'll just print out a little line here saying not running in Google Colab. We'll go can't use google.colab.files.download. Please download manually. Or please download foodvisionmini.zip manually. Now let's try this. Run that. We might get, if you've never seen this before, you might get a warning from Google Colab in your browser saying that it's trying to download some files. So I'm going to let this run and I'll come back once it's finished. So I'm going to pause the video here and I'll come back once this is finished downloading. If any errors come up, I'll let you know. Okay, so that took a couple of minutes on my end to download, but this is that warning I was showing you. If you run this, your browser, depending on your privacy settings, may want you to allow you to download files from Google Colab. It allowed it to work manually, so the one where I clicked on here and then clicked download, this worked. But because we're trying to do it programmatically, I'm going to click allow here. And yeah, see, we've got two copies here. The first one is when I went download and it started to work there. And then the second one is by running this code here. But truly, they actually contain they both contain the same files. So if we wanted to show all, we'll get out of that. I want to go to my local directory. So downloads, Food Vision Mini zip 1 and Food Vision Mini zip. If we go into that, there we go. We still got PyCache somehow. We may have to get rid of that, but these are the files we want to upload to Hugging Face Spaces. So we now have a guide to either upload via the web interface or upload via the command line or terminal. So if you want to try that out, give it a go. We've got the files ready to go. But in the next video, we're going to start working towards, well, actually, if you want to try running it locally, you can try that. But then we're going to start working towards uploading these files to Hugging Face. So try that out yourself if you want to. Otherwise, I'll see you in the next video and we'll deploy Food Vision Mini to the web for everyone to use. I'll see you there. Welcome back. In the last video, we downloaded our demo Food Vision Mini app to our local machine, and I've currently got mine in my downloads folder. See there, we've got it here. I've also got this other one because we downloaded it using two methods. One, the manual button clicking way, download from Colab, and this using code. Now, it might be slightly different if you're running this locally, but we're focused on Google Colab for now. Now, what would happen if you wanted to running our Gradio demo app locally? So you might want to test the app out locally before you upload it to Hugging Face Spaces. And you can do that. I've got some steps here prepared for you. We're going to focus on deploying to Hugging Face Spaces, but I've created these steps from running it locally on my Mac. Now, this may not work if you're on Windows. So if you have any suggestions, so running the app locally, if these steps don't work for you on Windows, please let me know through the GitHub discussions. You might have some steps that people can go through. And if you do have some steps like this, I'd love to link them and share them with others. So with that being said, let's now start to move towards 9.3, and that is uploading our Food Vision Mini Gradio demo to Hugging Face Spaces. Now, there's going to be a few steps involved in this, but there's nothing that we can't handle. So see the steps here. So I've already written these out, of course. So 9.3, we're just going to follow through these. So I'm going to get out of that. There we go. So step number 1 is sign up for a Hugging Face account. So I've already done that, of course. So if you want to, you can, I'm not going to click sign out, but if you go to Hugging Face, create account, call it what you want. I've linked mine with my GitHub, so all of my code and machine learning code is kind of synced. And then next is start a new Hugging Face space by clicking new space, which is what I've already done here. This is create a new space, but you can go down here, new space name. So this is going to be on my profile, Mr. D. Burke, and you can call this whatever you want. For example, Food Vision Mini. I'm going to call mine Food Vision Mini _video so that you know that this space was created during the video. License-wise, there are many different options that we could choose. Because our code is going to be open source, I'm going to choose MIT. And if you want to look up MIT license, I spelled that wrong, you can go here. There's a whole bunch of different open source licenses you could use. I've just seen MIT used a lot, so I'm going to use it too. Select the SDK. We're using Gradio, of course, but you can use Streamlit if you want, or even static HTML. And I'm going to keep mine public and then go create space. Beautiful, look at that. Food Vision Mini video. And there's nothing here yet except, of course, a README. We can adjust this to what we want. So there we go, SDK version. It's going to launch from app.py. The color we can adjust. Emoji. Fire is a pretty good emoji. And so if we go back to here, where's our app? We got a few options here. So it's saying that it's looking for an application file. And by default here, it's looking for app.py. Well, luckily, we've prepared an app.py earlier. So we've got app.py. Now, if we wanted to, we could upload this manually by going upload a file. Then we could click to drag and drop. So if I go to my downloads folder, Food Vision Mini, app.py, I could upload that manually, app.py, but I'm going to do this programmatically. So we're going to copy this, and again, all of these steps here, where are we up to? Select Gradio, click create space, clone the repo locally by running something like this. So yours might be a little bit different. I'm just going to move this over to here, move this over to here, get rid of that, get rid of that. This is what we're working towards. Food Vision Mini. That's a demo. There we go, all cleaned up. So clone it. Yours might look a little bit different to mine. I've called it Mr. D. Burke Food Vision Mini Video. Yours will be whatever it is, whatever you've called it. I'm going to come into terminal. Now, again, these are steps that are working on my Mac. You might have different steps if you're on Windows, and if you do, please let me know in the discussions. So I'm going to make a directory, mkdir, make directory, demos _ video. So this is going to house my demos from the video. So I'm going to change into that directory, ls. There's nothing in here, but now I'm going to go git clone. Oh, excuse me. I'm going to clone the repo that we just created from Hugging Face. So I've got this, git clone Hugging Face. Wonderful. There we go. ls Food Vision Mini cd Food Vision Mini video. ls, there's nothing in here except for a readme file. Wonderful. So what do we need to do next? So let's come over here. Let's say we've cloned the repo locally by something like that. We've done that. We could also upload the files manually by the Files and Versions tab. We've seen that. Number 9, copy/move the contents of the downloaded Food Vision Mini folder into the cloned repo folder. So this is where we're going to need to get the files from Food Vision Mini into our Food Vision Mini video demo file. So let's check ls downloads. There we go. So if I go, I might make this a bit bigger. So what I'm trying to do is copy these files into Food Vision Mini video. And you could do this by drag and dropping them. I'm going to try and do it programmatically. So ls downloads Food Vision Mini. What do we get? Okay. So I want to copy everything that's in here. I'm going to copy this file path using cp, and star into this directory. Let's see what happens. It's not a directory. Oh, is a directory, sorry. So this is where we need to do CP tag R for recursive into the current directory. So this is what it stands for. I'm in this Food Vision Mini video demo directory. Copy, recursive, everything in downloads Food Vision Mini, recursively with a star into dot stands for current directory into here. Let's run that. ls, what do I have? Look at that. Beautiful. So I have these files here. That's exactly what I want. I want to now upload everything that's in here to Hugging Face. And so if I do git remote v, which is going to tell me what my remote origin is, again, if you're not sure too much about Git, I've linked adequate resources to learn a bit more about it. But this is just saying that the remote repository that's stored on the cloud, huggingface.co/spaces, is this. So if I push files to there, they should appear here. They're not there yet, of course, because we haven't added them. But let's go back. What have we done so far? So copy, move the contents of the downloaded Food Vision Mini folder to the cloned folder. Yes, we've done that. Now, here's where git lfs comes in. To upload and track larger files, e.g. files over 10 megabytes in our case, which is our PyTorch model file, we need to install git lfs. So I've already installed this, but if you don't have it yet, you can run git lfs install. And then we can use git lfs, git large file storage, to track our large files. And git add.git attributes, which of course was already created by Hugging Face. There we go. So these are all typically larger files that you'll find with creating demo apps. So there's PyTorch.pth or .pt. And there's Pickle, which is another common Python file storage format. There's ONNX, Open Neural Network Exchange. So let's go back to our app. What do we want to do? We want to install git lfs. This is, again, step 10. So if we come back to terminal, git lfs installed. I've already installed it, so that's why I don't need to do it. And again, if you don't have it, if you can't run this command, you might have to install it like here. Brew install git lfs. And so now what we want to do is git lfs track our big files. So in our case, in the Food Vision Mini directory, track the files over 10 megabytes with git lfs. So we can do that git lfs track.file extension. And in our case, we want to track our fnetb2 PyTorch model file with git lfs track and then its file name. So let's bring that down into here. Boom. So now we're tracking our big file, our big model file with git large file storage. Recall that git is a file. It's going to track the changes in your files. So let's go git lfs track. We're also going to track.pth just to be safe, but it's going to say, oh, or actually, we want star.pth, so anything ending in pth. But yeah, it's going to say it's already supported. And what does it also say? Make sure your git attributes is tracked. Well, we're going to do that as well. We'll come back here. Tracked. We'll clear that. What do we have to do next? We've just done that step. Finally, we want to add the rest of the Food Vision Mini app files and commit them with git add star. Star means track everything. So git add everything to the git commit history. Git add star. Then we can go git status. What do we get? Look at all that. Beautiful. So we have a whole bunch of files here ready to be committed. So what we can do next is git commit with a message using the message tag. Let's go git commit message, and a common first thing to put is initial commit. Wonderful, look at that. Oh my gosh, we're one more command off deploying our app. So now we can upload or push the files to Hugging Face. So if we've done everything correctly, if we press or enter the command git push, they should all upload to here. Let's see it in action, hey? Git push. We'll let this run. There we go. So it's uploading LFS objects, so the large file system objects or large file storage. So this may take a little while depending on your internet connection, because our model file is 29 or 30 or thereabouts megabytes. So it's going to slowly upload here. I'm going to fast forward the video and I'll come back once this is finished uploading. If anything errors, I'll let you know. There we go. So that took about 2 or 3 minutes on my machine. So it looks like everything has been added correctly to Hugging Face Spaces. Mr. D. Burke Food Vision Mini video. Wonderful. So let's see what happens here if we refresh. Oh, building. Look at that. All of our files are here. This is so exciting. So once this building has finished, our Food Vision Mini app should be deployed on Hugging Face Spaces. And of course, we can see the logs. This is what's happening behind the scenes. Hugging Face is installing all of the dependencies. There we go. Successfully built all these things. Torch Vision, Matplotlib, all those dependencies that our app needs. Gradio as well. Now if we come back here, you may see this may look different in the future as Hugging Face update what they offer. There we go. Oh, what's going on? Let's refresh. Do we have running? Not just yet. Okay, I'm going to leave this video on a cliffhanger and it's going to be building. And in the next video, it might be finished. It may take a couple of minutes. If anything goes wrong, I'll let you know. But I'll see you in the next video. We may have Food Vision Mini video deployed and ready to go. Welcome back. In the last video, we pushed all of these magnificent files to Hugging Face Spaces with the hopes of deploying our Food Vision Mini app. And at the moment, mine's still in the building phase, but let's click refresh and see what we've got. No errors. Still building. Do we have an app? Okay. We'll refresh and then come over here, pushing image. Oh, what have we get? We've got something wrong here. Currently, only the default theme is supported. Caching examples here. Okay, I think that is not too bad. I think it's still building. Oh my gosh, we're about to see a live deployment. Once this is ready, if this errors out, it's actually going to say some sort of error, and we should get the log in here. But if we keep going, oh, there we go. Of course, we get an error. App.py demo launch, print errors locally. Okay. Share is not supported when you are in Spaces. Okay, so we got something wrong in our app.py, which is absolutely no worries. I'm actually glad that we got this wrong because you can see that we can fix this by going edit. So all I did was files and versions. So this is what we've just uploaded. You can edit this from here. We go in here, share equals true. We don't need this in our deployed version. So debug equals false. And I'll write here, don't need share equals true in Hugging Face Spaces. And then we should go here, fix app.py to remove share equals true. And then once we commit these changes, it should try to rebuild. There we go, building. Now this may take another couple of minutes, so rather than sit here and wait for it, yeah, there we go, pushing image. This should be quite quick now actually because it's cached. Once you do your first build, Hugging Face will cache everything behind the scenes and subsequent builds should be a bit quicker. So I'm gonna let this run, I'll pause the video and then I'll come back once it's working or if there's another error. All right, I'm back. So I've let this run for about 2 or 3 minutes now. So let's refresh and see what we got. Okay, there we go. Beautiful. Caching examples. To create a public link, set share equals true and launch. We don't necessarily need that because we're running in Hugging Face spaces. Now let's come back to here. Running, that is beautiful. We've got green. We've got green, everyone. Let's see. Let's go to our app, Food Vision Mini. Do we have a demo or the video version? Wonderful. Look at that. All lights are go. Let's see what happens. Pizza, beautiful. Steak, sushi, clear, wonderful. Let's try upload a custom image. So if I go into my Dropbox, I've got some food images saved here. And then number 10 is steak. Let's try that out. What do we get? Processing steak. Beautiful. Of course, you can try this out. And in fact, I'd love to see your own examples. Please share them with me at GitHub. And you can post them in the discussions or on the Discord or something like that. If you do face any errors deploying this, because there was quite a few steps to go through, please also let me know if something didn't work on maybe a Windows machine. I'd love to share the solution with other people. But the final thing we can do is we can embed our Gradio demo in our notebook. So let's see that in action. And we need the URL to look a little bit like that. So maybe I copy this. So these are all the steps that we just went through to uploading to Hugging Face. And I'm glad we faced an error because we saw how we could fix it on the fly. And why don't we fix it in our notebook as well? So our error was in here. We don't actually need any of this. We could just go launch and that will fix it up, overriding that. And then we can override that and then re-download the uploaded files or the updated files, sorry. And just remember, because we've turned this into a Git repo, Food Vision Mini Video, if we now go git pull, it's going to pull down our changes to app.py. So that was the change that we just made manually by going into files and versions, app.py, and we changed that. So now that change is reflected in our local directory. And of course, if we wanted to edit this Food Vision Mini Video, any of the files in here, we could do so locally and then push the changes back up to here. But since we've been working in Google Colab, let's continue there. I've now got a fun way of sharing your Hugging Face demos from a notebook. You can do it with an iframe. So IPython is what Jupyter notebooks used to be called, but there's a display module and you can import iframe. So if we look up what is an iframe in HTML, it's a frame to embed some kind of widget. So if you want to look up more, you can go for that. But this is again from the Gradio docs, Gradio share demo, sharing your app. There's many different ways to do so. Hosting on Hugging Face Spaces, that's just what we've done. And here's what we're going, embedding hosted spaces. So this is what we want to do. And I'm going to write here, we can also share our app by embedding it. So if we change this, we need it at the URL in a special format. So hf.space/embed/Mr. D. Burke Food Vision Mini. That's the Food Vision Mini demo I created earlier, but now I'm going to append the video tag so you know that I'm going to not be hosting this one, which was the original Food Vision Mini. I'm going to be hosting this one, or embedding, sorry. So now if we come to my profile, I've got 3. There may be more by the time you watch this. So Food Vision Mini Video, this is what we've just deployed together. I'm going to copy this. I'm going to bring it in here. Oh, I don't need to actually. I've got that URL there. You might want to change yours to have your username and then your repo name. But let's see what this looks like. Beautiful. So this is pulling it straight from Hugging Face Spaces. So if you wanted to create a portfolio where you could share your demos, you could do it like this. So you could have a notebook just exactly like what we've done here, training a model, explaining what you've done experiment-wise, and then here you can have a section for people to try out your model. So if we try it out, it's going to work exactly the same as if we were to run it directly on Hugging Face. Look at that. How beautiful is that? Try it with your own images. Please share them with me. I would love to see it. But that is sharing and uploading our Food Vision Mini demo. Now, we're not quite finished Milestone Project 3 yet, although we quite well could finish there. We've built Food Vision Mini. I think it's time to step things up a notch. We're getting pretty good with this machine learning thing. How about we increase Food Vision Mini to a larger size? But no spoilers, we'll cover that in the next video. I'll see you there. Welcome back. In the last video, we got our Food Vision Mini model deployed. And we saw how well it works. Let's just try it one more time while we're here. There's the photo, Pizza Dad. We've been testing all throughout the course. So let's see. I love this anticipation moment. How's our model going to go? Remember, a lot of this is due to the fact we had to upload the image. There we go. Pizza. Beautiful. We see the actual prediction time is quite quick. So what do we do now? Well, if you shared this with a friend, they could of course try it, but the classifier is only going to work on images of pizza, steak, or sushi. And so this is Food Vision Mini. And where did this dataset originally come from? Well, of course, it's a subset of Food 101. There's TensorFlow datasets, it's from Kaggle, Papers with Code, Hugging Face has it, Torch Vision, this is where we got our one from. But what is it? The Food 101 dataset is a challenging dataset of 101 food categories. So we're only using 3 out of 101 categories. So while we're here and while we've got such good momentum, how about we step things up a notch? So this is the surprise I hinted at right at the start of the course, of this section that is, model deployment. Let's create Food Vision Big. And Food Vision Big is, well, Food Vision Mini works well with 3 classes: pizza, steak, sushi. So all of our experimenting is paying off. That's truly what we've been doing this whole time, is running small scale experiments to make sure it works so that we can step things up a notch and go to Food Vision Big. So let's step things up a notch and make Food Vision Big using all of the Food 101 classes. This is going to be our biggest model of the whole course. So let's jump into a keynote. This is what we've done with Gradio so far. We're going to replicate the same workflow that we did for Food Vision Mini and deploy it to Hugging Face Spaces with a Gradio app, but with a Food Vision Big model. So we've got Food Vision Mini, and now we're going to Food Vision Big. So of course, Food Vision Mini uses 3 classes, and we've seen it to work quite well with our FNet B2 feature extractor model. However, it's time to step things up a notch and go to Food Vision Big, which is of course going to add more classes such as burger, chicken wings, gnocchi, apple pie, ramen, tacos, gyoza, paella, pancakes, chicken curry, ribs, 101 different classes. So let's get started, hey? Well, actually, I think the first thing we need to do is build a model. So let's go to 10.1 and we'll create a model for Food Vision Big. And in fact, I'm going to let you give that a shot, plus transforms. So we've already got, let's use our FNet B2 feature extractor. But if we've got 101 different classes and we come up here to our function for creating an FNet B2 feature extractor in 3.1, we used this function to create a model for Food Vision Mini, which created a model with 3 classes. So if now we're working towards creating a model with 101 classes, how would we use our function create FNet B2 model for creating a model that's capable of fitting on 101 classes? So I'll let you give that a shot, and in the next video, we're going to create Food Vision Big, our biggest model yet, together. I'll see you there. Welcome back. In the last video, I revealed the big surprise, Food Vision Big, that we're going to be working on to complete this milestone project 3, PyTorch model deployment. And so by the end of this section 10 and 11, we're going to have an equivalent demo here of Food Vision Mini, but for Food Vision Big, a model capable of classifying 101 different classes of food. So let's go here. You might have already created this. In the last video, I challenged you to use our function create FNet B2 to make a model capable of fitting 101 different classes. So I'm going to call mine FNet B2 Food 101 so that we know it is capable of fitting 101 different classes. The transforms are going to stay the same. So I'm going to write down here, create Food 101 model and transforms. Now, the beautiful thing, thanks to our function that we wrote before, all we have to do is set number of classes equal to 101. And let's now get a summary. I'm going to find summary in the notebook. I'll go, we've done this a few times. Yeah, I'll get this one. This is from right up the top here, FNet B2 feature extractor. Come down, let's print a summary to make sure that this model is capable of fitting 101 classes. So Food 101, there we go. I'm just going to make a bit more space over here. So we have the same input shape, and there we go. Look at the output shape, 101. That is, of course, because we set num classes equal to 101. And just as we want, all of the base layers are untrainable, so they're frozen, except for the output layer here. We have a sequential classifier which has 101 output classes, which is exactly what we want for Food 101. And now, you might notice that there's a lot more parameters here in the final layer than our previous model. Now, why is that? Well, that's because we've got 101 classes rather than just 3. So if we copy this code down here, and if we go, instead of FNet Food 101, we want FNet B2. So this only has 3 output classes, so therefore only has just over 4,000 trainable parameters. So of course, more output features in the final layer equals more trainable parameters. So we've got our model. Now we might do one thing to adjust the transforms. So let's have a look at this. FNet B2 transforms. What we might do is add in some data augmentation to this transform. Now, why do I say that? Well, let's have a look at the Food 101 dataset. So Food 101 Torch. This is what we're going to be doing, downloading this dataset. And so we're now going to step things up and working with over 100,000 images. Whereas previously, or in fact, spoiler alert, we're going to only use a subset of this as well to keep our experiments quick. If you'd like to experiment on all of these, I would 100% encourage you to do so. But when we're working with such a large amount of data, it's a tendency for our neural networks to overfit. So if we go to learnpytorch.io, what is overfitting? Number 4, I believe, is where we covered that topic. And then number 8, overfitting, right? So the training loss ends up being lower than the test loss. So that's overfitting. That's because we have so much data that our model is learning the training data set too well and not generalizing to the test data set. But of course, we have some techniques to deal with overfitting. And the most common technique of preventing overfitting, well, the technique is known as regularization. So you want to regularize your model. And I have a little bit of trouble saying this word. But here are some ways that we can regularize our model, get more data, simplify your model, or use data augmentation. This is probably one of the easiest ways. Aside from transfer learning, we've already seen this in practice. This is what we're already doing. But why would we use data augmentation? Well, these are some things, tricks of the trade that you kind of pick up along your journey in machine learning. And one of the ways to do so is read how other people have done things. So this is from Torch Vision, the Torch Vision team, how they trained their pre-trained models in the Torch Vision package. So if we scroll down here, they have a list of techniques that they used. And so here's a fair few. We're not going to go through all of them, but there's learning rate optimizations, trivial augment. So this is what I mean by data augmentation. We saw this way back in maybe section 4 or section 3 using trivial augment, but now we're working with such a data set, we're going to reintroduce it. Long training is another option if you wanted to try training your models for longer. We've seen that before. Random erasing, label smoothing, we're going to see that one later on, that's a spoiler. Mix up, cut mix, weight decay, fixed res mitigations, exponential moving average, or that maybe not exponential. Is it exponential? Yeah, it is. Exponential moving average. Wow. I know a few more acronyms than I give myself credit for. And then inference resize. So of course, I'll let you read through this, but let's come back to here and I'll write a little note. Since we're working with a larger data set, so this is where your mind should go. We may want to introduce some data augmentation techniques. And of course, we could try to train our model without data augmentation first, but because this is a machine learning cooking show, I've tried this and I found data augmentation helps. You could try it without. So we may want to introduce some data augmentation techniques. This is because with larger data sets and larger models, overfitting becomes more of a problem. Not always the case. Again, a lot of the statements in machine learning are quite general and they take some experimentation. So because we're working with a large number of classes, let's use trivial augment as our data augmentation layer. Beautiful. Or as our data augmentation technique. There we go. That's probably more precise. And then for a list of state-of-the-art computer vision recipes. Now, of course, this is computer vision specific, but what you'll often find is there are a lot of these style recipes for many different problems. So for natural language processing, you would still ask the same question. Can we use a pre-trained model? Are there forms of augmentation? And pre-trained models for natural language processing, you'll probably find on Hugging Face Hub. But we're getting beside the point here. We want to work on Food Vision Big. So let's do that. We can adjust our transforms by going Food 101 transforms equals Torch Vision .transforms.compose, and I'm going to put in a list here. We will use trivial augment wide first. So Torch Vision .transforms, and then this is trivial augment wide. Beautiful. So let's now see what this looks like. Food 101 transforms. Wonderful. So that's going to be our training data transform. So create training data transform. Because we've got way more classes and way more data, we introduce data augmentation so that hopefully our models don't overfit. We'll see this in practice later on. And then, of course, I might just print this one out up here. And then for the testing data, we're just going to use the original FNet B2 transform. This is our testing data transform because we don't we don't want to augment our testing data or inference data. So recall the purpose of data augmentation, if we go back here, is to manipulate the training data in a way so that it's harder for the model to learn as it artificially adds more variety to the data. So it does that by manipulating the input images. So there's some transforms and a model ready to go. What do we need next? Well, we need a data set for Food Vision Big. So I'm going to write down here, getting data for Food Vision Big, and you might want to give this a shot. The class that we're going to use is from torchvision.datasets. We're going to download the whole Food 101 dataset to our Colab notebook. So get the Food 101 dataset, give that a shot, and we'll download the biggest dataset we've worked with so far. in the next video. Welcome back. So we're working towards creating Food Vision Big. And in the last video, I challenged you to download the Food 101 dataset. So I trust you gave it a go. There's a different section of the dataset for training and test data. So that may have been the little trick you might have stumbled upon, because I know I definitely have. So let's, from Torch Vision, import datasets. And we're going to set up our data directory. Even though we already have one, we're going to do it anyway. So from pathlib, import path, and our data dir is going to be, of course, path data. And then we can get the training data. So get the training data. So this is going to be, if we read into the documentation, it's 750 images times 101 classes. So that is 75,750 times 101, 75,750 training images. And then the testing data set is 250 images per class times 101, which gives us 25,250. Add those together, we have 101,000 total images. So train data equals datasets dot food 101. The root is going to be data dir, and then split equals train, and then transform. So this is where we want to pass in our training transform that we created before. Food 101 transforms. That's going to apply data augmentation to the training data, which is what we want. Oh, excuse me. I just want to go Food 101 train transforms. So I'll write a little note here. Apply data augmentation to training data. Then what do we need next? Well, we can pass in the download tag or download bool parameter. Download equals true. So what's happened here? Food 101 transforms. Oh, I'm going to call these train transforms so it's a little bit more clear that we know that they are for the training data. Yeah, there we go. Okay. So now we're also going to get the testing data. Get the testing data. So this is 250 times, I might go 250 images. Images times 101 classes. And then we'll go test data equals datasets dot food 101. The root is going to be our data directory, which is of course just the data file. And then I'm going to set the split. The split I want to download for the test data is of course the test data. And then the transforms here, or the transform, sorry, is going to just be the plain old fnet b2 transform, rather than the train transforms, which include data augmentation. So I'll write down here, don't perform data augmentation on the test data. We don't do data augmentation on the test data generally because the test data emulates data we've never seen before. So we're trying to emulate with the test data from the real world. So download equals true. So who's ready to download the biggest data set we've downloaded so far? Let's do it, hey? In 3, 2, 1. Now, because this is going to download so many images, 101,000 to be precise, it might take a little while. So yeah, see, we're getting a time limit of about 5 minutes to download to Google Colab. Now, of course, this will depend on a number of things, such as where your data is being hosted or where your Colab notebook is being hosted on the cloud. So I'm just going to let this run. And over here, we're going to get a file. Yeah, there we go. food101.tar.gz. So this is going to be like a compressed file. And then this functionality here we've written from torchvision.datasets is going to not only download it, but also unzip it. So we'll see what that looks like in a second. But you could do this process of what we're doing for Food Vision Big for almost any data set in Torch Vision datasets. And what I mean by that is if you wanted to try starting working on your own problems, we've focused on Food Vision, but there are a lot of data sets in here that you could work with to practice your computer vision skills. So there's Flowers 102 if you like flowers. That's a similar data set to Food 101, except classification with flowers rather than food, and a whole bunch more. So check out those data sets. That's one of the best ways to practice your skills, is to download a data set and then start running a series of modeling experiments, just like we've done throughout the whole course. And finally, rather than wait here for this to download, I'm going to let it download in the background, and I'll come back once it's finished, and if anything errors, I'll let you know. And we're done. The magic of cinematography. So as you saw here, or as you can see here, it took me about 5 or just under 6 minutes to download it, but to unzip it and whatnot, Colab's telling me this cell took about just over 7 minutes, but that's not too bad to get a data set of 100,000 images for free. So now we've got Food 101, and then we have all of the images in here. Look at all those classes. Apple pie, baby back ribs, baklava, beef carpaccio, maybe I'm saying that wrong. Beef tartare, beet salad, bajonette. What's a bajonette? Well, let's get our class names variable, hey? Get Food 101 class names, and forgive me if bajonette is one of your favorite food, or if I'm not even saying it correctly. But let's go train data.classes. This is going to give us a list of class names. So we'll view the first 10. Food 101 class names. Perhaps your favorite food is in this list. There we go. Apple pie, baby back ribs, all those ones we went through before. Churros, clam chowder, cupcakes. Oh, I love cupcakes. Donuts, eggs benedict, filet mignon, fish and chips, frozen yogurt, fried rice. Okay, this is going to be much more exciting when we deploy it as Food Vision Big. There's a fair few different classes here. Guacamole, gyoza, hamburger. Okay, that's enough. I want to look up what beijonettes are. What's a beijonette? Oh, they look delicious. Fried dough food. Beijonette is a type of fritter or deep fried pastry, usually made from yeast dough in France. Oh my gosh, delicious. Okay, I'm a fan of beijonettes. So, all right, let's stop doing that. We've got a data set. So now what do we have to do? Well, how about, this is 101,000 samples. But to keep our experiments quick, again, we're not stopping experimenting just because we're in Milestone Project 3. Let's create a subset of this data set so that we're not trying to fit on 101,000 examples. We can train a model quite quickly, deploy it, see if it works. If it works, we can then, of course, come back and train it on all of the data. So that's what we'll do in the next video. We'll create a subset of the entire Food 101 data set. I'll see you there. Friends, welcome back. In the last video, we downloaded the entire Food 101 dataset, training data and testing data, and we see now that there's a lot more food classes here for our model to learn. So this is going to be quite exciting when we eventually deploy it, because people could try it on a lot of different dishes. So let's now move towards, we've got 101,000 images. But to keep things quick as well when we want to keep experimenting, let's now create a subset of the Food 101 dataset for faster experimenting. Now, why create a subset? So we want since we've never trained a model on all of Food 101, we want our first few experiments to run as quick as possible. So we know Food Vision Mini works pretty well, but this is the first time we've upgraded to 101 classes. So we're putting on our machine learning engineer's hat here. We're working for a food vision company. Our prototype works. Food Vision Mini works great. Now we want to step things up a notch. So to do so, let's make, how much should we do? We did 20% for Food Vision Mini, so let's do that the same again here. Let's make a subset of 20% of the data from the Food 101 data set. Training and test. And in fact, let's make a short-term goal. So let's look up the Food 101 paper. So this is where the data set originally came from. Food 101. It's a PDF paper. So where was it from? ETH Zurich. So what do we get here? If we look into the results they got, with an average accuracy of 50.76%. So I believe that's not the highest value they got though. They used a CNN. You can read this paper if you like to look at where all of the data set originally came from. They originally used a random forest model, but this paper's about 10 years or so old now at the time of recording. So we want to see if we can introduce some modern techniques to beat the results that they got. And that's in fact one of the best ways to practice machine learning, is to find something that exists in public, a data set, and then use what you've learned to try and beat the results. Here we go. CNN. So when they used a convolutional neural network, their results, they got 56.4% accuracy. So this is our benchmark for deploying our model. We want to beat the original Food 101 paper result of 56.4% accuracy on the test data set. And then see the paper. I'm just going to link this in here. So that's our interim goal. But of course, we'd rather deploy it as well. Beating it is just going to be a bonus. And let's go. We want to beat this result using modern deep learning techniques and only 20% of the data. So that is our challenge. We want to use 1/5 of the data the original paper used and beat their result on the test data set. And we've got a little bit of advantage because we get to use modern deep learning networks and a few other things. So with that being said, I just want to give a quick overview of the data sets we're using / we've used throughout the course. So this is the overall theme. Our motto is experiment, experiment, experiment. So not only with model size, we've been experimenting with data set size. So we kept our experiments small and quick for the majority of the start of the course. Only 225 training images and 75 testing images. Now we're up to section number 9. We're going to create a subset called Food Vision Big 20% data, which is of course a custom split of Food 101 with 101 classes rather than 3. So that's a big upgrade here. And then of course, we're going to go from 450 images to 15,000 or just over training images, and from 150 testing images to just over 5,000. And now my challenge to you is, after we've worked through this problem, to go on and do the extension on your own, train Food Vision Big on all of the data. But let's not get ahead of ourselves. Let's create a sub-split for our notebook. And to do so, we can use Torch. Has a helpful function from torch.utils. We have .data and then import random split. And so if we look up torch random split, what does this do? Here we go. At the heart of PyTorch data loading utility is the torch utils. Oh, we don't want that. We want random split. There we go. Randomly split a data set into non-overlapping new data sets of given lengths. So this is exactly what we want. So if we passed in a data set here, the data set to be split, and then 2 different lengths, so the lengths of splits to be produced, we could do more because this takes a sequence. So let's just say our first split would be 20% of the length of this input data set. And the second data set, or the second split, would be the remainder of what's in this. So if this is 20%, the remainder would of course be 80%. And you could extrapolate that out. You could make the first one 10% and the second one 90%. The caveat here is that these both splits together, the lengths must equal the total of this. So if range is 10, 3 plus 7 equals 10. And if ours is 100,000 and the first split is 20,000, the next split must be 80,000, or 20% and 80%. So that's the caveat there. But let's put this into a function, hey, to create some data splits. Random split, and then I'm going to just link to here. Documentation. Beautiful. How can we do this? Maybe we go def split data set, and of course it's going to take in a data set which will be of type torchvision.datasets. And then let's go split size. So we'll define what the split size is, will be a float because we want to define it in percentages. And we'll start with a default of 20% or 0.2. And then finally, we'll set up a seed parameter for reproducibility, because if we're going to be randomly splitting our data set, here we go, there's a generator here, which is used for the random permutation, which is what we can do torch manual seed. So we don't necessarily have to set that, but because we've been using manual seed of 42 throughout the whole course, we might as well do it here so that my split is as close as possible to what your split is going to be on your screen. So let's create split lengths to begin with, based on the original data set length. We want length number 1 is going to be equal to an integer, which is the length of the input data set, which of course for our train data right now with Food 101 is going to be 75,000, and the length of our test data is going to be 25,000. And then if we just multiply this by 0.2, what do we get? There we go. So that's our 20% splits. So we have length data set, and then we want to turn it into an integer. So we're going to feed in here split size. And of course, by default, split size will be 0.2. And then length number 2 can be, let's just go length data set minus length 1. So this is just the remaining length. And because split data set, or random split, sorry, takes in a sequence here, this could actually be more than 2 lengths, but we only need 2. So you could have 3, you could have 4, you could have 5 if you wanted to create different subsets of your data set and test your model on those. So let's now print out some info. Print out info. You know how much I love to print out info. Info. There we go. Oh my goodness. My fingers aren't warmed up this morning. Just did the exact same typo 3 times in a row. Splitting data set of length. Let's go len data set. So this is the length of the entire data set into splits of size. The first one is length 1 and length 2. That'll do for that. And then we can go, let's create some random splits here. Create splits with given random seed. And I'm going to go random split number 1, random split number 2 is equal to torch.utils.data.random split. I could just use this above, but I'm just going to type it out for completeness. So we want data set. So this is going to be the target data set, of course. We passed it in there. And then we also need our lengths, which is going to be a sequence of the 2 lengths that we created above. Length 1, length 2, and then if you had length 3, of course, you could pass that in here. Just remember, the caveat is that the total lengths of these values here must equal the overall length of this. So for ours, it works with length 1 and length 2. And then finally, we're going to pass in the generator, which will be torch.manual seed, and then our seed of default 42. Finally, we can return random split 1 and random split 2. Wonderful. So let's test out our function, hey? So I'm going to create training 20% split of Food 101. So we're going to use this function on both the training and the testing data. So train data, I'm going to call this train data Food 101 20%, be a bit verbose here. Because it's going to return a tuple, this returns a tuple of random split 1, random split 2. I'm only interested in random split 1, which is, of course, this is defaults to 20% data split. So I'm only interested in that first one. Of course, this size would change if we manipulated this. So I'm going to set this equal to split data set, our function, and the data set is of course going to be train data, and the split size, we don't need to code this in, but we're going to anyway, is 20%. And then I'm going to do the same thing for the testing data. So create testing split Food 101, 20%, test data Food 101, 20%, equals here. Now, just recall, we're doing this, we're making a smaller data set. We don't necessarily have to. We could test across the whole data set, but that may take a while for our model to fit. We're creating a smaller subset so that we can test our model out to see how it goes on 101 classes before we train on the whole data set. Oh, excuse me. Split data set. That's what our function is actually called. And let's run this. Beautiful, there we go. Okay, so now let's have a look at the length of our data sets. Train data food 101, just to make sure. So the whole motto here is start small and increase your experiment size when necessary. Beautiful. That is exactly what we wanted. That is in line with what we've said here. Number 9, food vision big, 20% data. We have 15,150 training images and 5,050 testing images. That is going to be, or these are going to be our data sets for training our model for food vision big. So with that being said, oh, we've got one more step, don't we? We need to, in the next video, you might want to give this a shot, is turning our Food 101 data sets into data loaders. So we've got data sets, but let's now convert them into data loaders so that we can feed them to our model. So give that a shot, and I'll see you in the next video. Welcome back. In the last video, we created a smaller subset of the entire Food 101 dataset. And we do this because we want to make sure our experiments run quickly. We could jump in and start modeling on the entire Food 101 dataset, but I'd like to leave that as an extension for you to try. So to begin, before we deploy a model to Hugging Face Spaces, Food Vision Big, we're going to train an FNet B2 feature extractor on 15,000 or just over 15,000 training images and evaluate it on 5,050 testing images. So now we're up to turning our Food 101 datasets into data loaders. So let's import Torch. This one, I gave you the challenge of giving it a shot in the last video. It may have tripped you up a little bit because previously we've used our going modular script to do this, to create our data loaders, datasetup.py. However, because our datasets are in the form of datasets right now, well, that doesn't really, it makes sense. It doesn't really, but it does. We can't use our create data loaders function that we've used previously because these are already datasets. They're not in folders. We don't have to import them. So we can go the old traditional route, and that's by creating a batch size of 32, and then we can create the Food 101 20% training data loader by going train data loader Food 101 20% equals torch.utils.data.data loader. Oh, we haven't typed that in a while. And then we can pass in the data set. So if I push Shift Tab here, we should get a doc string. There we go. The data set is, our Torch data set is, of course, our train data Food 101 20%. And then what's next? Our batch size is equal to, our batch size will stick with 32. If you do get a memory error when we're working with such a large data set, you can lower your batch size. So you could go divided by 2 or something like that. That's one way to, if you ever get like a GPU memory error, lowering the batch size is one way to handle that. But we should be fine with a batch size of 32. And then we're going to go shuffle equals true. We want to shuffle the training data. Finally, we'll set number of workers. Maybe we'll do it to, I'd like to set it to import OS. And let's go num workers equals, now this is a heavily debated topic. If we go import OS of what to set it to, CPU count, usually it's 2 per GPU that you have access to. Yeah, 2. So, or 4, so between 2 and 4 is usually a good value, or 1, so it's default 0. 1 is also a good value, 2, another good value, and then 4 is also apparently a good value. So the reason why I know this is because if you go PyTorch what to set num workers to, Now, of course, this is very experimental. It will differ on the hardware. It will differ on guidelines for assigning num workers, PyTorch num workers, a tip for speedy training. Yeah, they said the best value is 2, but yeah, there's some arguments. This is not very practical. I'll let you read more into that. But the rule of thumb that I've kind of found is 2 per GPU, and CPU count, we've got 2 CPUs. So again, experiment with this. We're going to stick with using 2 for now. And then let's go create food 101. I'm going to put up here 20%. 20% testing data loader, that is. So test data loader food 101 20% equals torch.utils.data loader. Then of course the data set is test data food 101 20%. Oh guys, we're getting so close to training our biggest model yet. Batch size, and then we're not going to shuffle the testing data. We don't need to. False, that doesn't need to be all caps, but the next one does. Num workers equals num workers. Beautiful. And I'm just going to put a little note here. So this value is very experimental, just like many different hyperparameters in machine learning, right? And the best value will differ depending on the hardware you're using. Search PyTorch num workers setting for more. And of course, if you wanted to find out in the documentation, what does that actually do? Well, let's Google this. This is what I do to learn things, or learn more things. Where do we have num workers? There we go. So PyTorch provides an easy switch to perform multi-process data loading by simply setting the argument num workers to a positive integer. So 0 will not use multi-process data loading, but setting it to a value above 0, so any positive integer, will start to use multi-process data loading. However, what I've found is that it saturates at a certain point. So once you get over 4, again, this will be very experimental in my experience. Over 4, the returns are diminishing, but it will depend on the hardware you're using. So just keep that in mind. We'll get out of all this extra jazz. Beautiful. Let's create some data loaders. Now we'll check the length of these to see how many batches we have. And then len. Beautiful. So we have 474 batches of about 32. There might be some overlap for the training data loader, and 158 batches of images for the testing data loader. So I think we've got all the pieces of the puzzle ready to start training. In fact, you might want to give that a go. So in the next video, let's work together to train our biggest model yet, training Food Vision Big. Beautiful. So we've got all the scripts ready to go for that in Going Modular. Engine.py is where you want to look. So give that a shot. Train the biggest model we've ever trained so far. And I think 5 epochs should be enough, because it might take a little while to train. But we'll see that in the next video. All right. Put your hand up if you're ready to train Food Vision Big. You might have already given this a shot, but let's do it together. So this is going to be the biggest model we've trained so far. So things for training, what do we want to do? Well, we'll keep experiments short. We'll go 5 epochs to begin with. We can always increase this if we find good results. The next one is going to be our optimizer, which is going to be torch.optim.atom with LR equals 1E negative 3. And then our loss function, here's a little trick I'm going to introduce here as well. So you might have already used this loss function, torch cross entropy loss, but I'm going to introduce the technique of label smoothing. And label smoothing is a very powerful regionalization technique that comes basically for free. So that means we can just implement it like that, and it's going to help prevent our model from overfitting. Now, of course, where could we find out what is label smoothing? What is label smoothing? To smooth or not, what is label smoothing? Okay, we've got a good resource there, or potentially good resource. Papers with Code always has great explanations of things. Label smoothing is a regularization technique. Regularization is what? Prevention of overfitting that introduces noises for the labels. This accounts for the fact that datasets may have mistakes in them, so maximizing the likely of log probability y given x directly can be harmful. So there's some more information there, but if we go into another resource, so this is from Yushong Wang. What is label smoothing? A technique to make your model less overconfident. So if we go down, I like this part at the end here. When do we use label smoothing? Whenever a classification neural network suffers from overfitting and or overconfidence, we can try label smoothing. So right now, we don't know whether our model is going to overfit or not. But because this is a machine learning cooking show, I have already tried to fit a model without label smoothing. And I can tell you that using label smoothing helps because we have so many classes. We have 101. And you might be thinking, well, Daniel, where do you get these things from? Well, we've seen, if we go to PyTorch state of the art, we've seen this one already, state of the art training, the blog post. So this is where machine learning is part cooking, part science, is that a lot of the time it's by experimenting and trying different things. So here's label smoothing. I chose to use label smoothing out of all of these because like trivial augment, it's one of the easiest to implement. We can get away with it by going torch and then cross entropy loss with a single parameter. Label smoothing equals something. And Torch, what did they use? The Torch Vision team. If we look for label smoothing, what was the value they used? There we go. Label smoothing equals 0.1. We use PyTorch's newly introduced cross-entropy loss label smoothing parameter, and that increases our accuracy by an additional 0.13 or 318 points. Now, of course, that's on ImageNet. So let's give it a shot trying it out for our own problem. We'll come back here. Label smoothing. So first and foremost, what do we need to do? Or actually, let me give you another little overview of what it will do. So why use label smoothing? This is another bit of intuition. So label smoothing helps to prevent overfitting. It's a regularization technique. So if you were to go and further research it, you would probably find something without label smoothing and 5 classes. I'm only using 5 as a demonstration purpose, but this will go for any arbitrary number of classes. Your model output might be something like, or prediction probabilities after we've gone through softmax, might be something like this, 0.99. So it's very confident on the middle class and basically assigning nothing to the other classes. So what can happen sometimes with neural networks is because they're so powerful, they become overconfident on one particular class. So what label smoothing tries to do is it does this. With label smoothing and 5 classes, the output of your softmax layer might be something like this, 0.01, 0.01, 0.96, 0.01, 0.01. You see what it's done here? It's smoothed out the overconfidence. So it's taken from here and assigned some values to the other labels. So this helps to prevent overfitting. Again, it's not guaranteed, but it's one technique to try to do. Helps overfitting to stop the model from getting too confident on a single class and at least assigning some prediction probability or at least considering another class as an option. So that's the crux of label smoothing. But of course, if you want to do your own research and learn a bit more, you're more than welcome to do that. Let's see it in action. So from going modular, let's train the biggest model we've trained so far. Going modular, import engine, and then we're going to set up the optimizer. optimizer equals torch.optim.atom, params equals fnet b2. We want to optimize the food 101 parameters, of course. And then our learning rate is going to be 1e negative 3. And then we're going to set up the loss. This is where we're going to introduce that new label smoothing parameter, which is generally helpful for when you have a large number of classes. Torch.nn cross entropy loss, and we can just implement it just like that. Label smoothing equals 0.1, and then let's go. Our goal is we want to beat the original Food 101 paper's result of 54 or 56.4% accuracy on the test data set with 20% of the data. And if you're paying close attention, you might notice that the Food 101 paper achieved this result on 100% of the test data. So truly, we're not really comparing our model as apples to apples when we train on and evaluate on 20% of the Food 101 data. But we're going to see how it goes. And then, of course, later on, you can train this model on the whole Food 101 data if it goes well. If it goes well, that is. No spoilers. So we're passing in our train data loader here, Food 101 20%. Then we can do the same with the test data loader, equals test data loader, Food 101 20%. And why is that telling me I've got an error? Is there a typo there? Colab, you couldn't keep up with my fast typing. The optimizer equals optimizer. Our loss function equals our loss function. Epochs equals 5. And device equals device. Now, once we run this, it may be running for a while. So I just want to highlight the fact of what GPU I have access to. Now, this should run on almost any GPU, but I have quite a, because I'm using the paid version of Google Colab, I have quite a good GPU here in the Tesla P100. So if you're using the free version, this should still work. It just may take longer to train. If you're running this locally as well, depending on the hardware you have, will depend on how long this model takes to train. Because after all, we are training on 20,000 plus images. So you ready to go? We're going to bring Food Vision big. We're going to train our biggest model yet. In 3, 2, 1, let's go. Oh no. Here we go. So we're not going to know how long it's going to take for a while until it's finished one epoch. But the good news is we've got no errors so far, so it's going through the train step function, get data, try get data, etc., etc. Train step, beautiful. So it's training, wonderful. It looks like our model is working behind the scenes. Now, while we wait for our first epoch to finish, how about we start preparing some of the next sections? So of course, we want to inspect the loss curves of our Food Vision big model. And how do we do that? Well, we can go from helper functions, just like we've done before, import plot loss curves, and then we can go plot loss curves. So we'll get all this ready ahead of time, hey? Food 101 results. Just while we're waiting for the first epoch to come up, then we'll have a little bit of an idea how long this model will take to train. Then let's get the next one ready. What will we want to do? Well, if our model is performing well, we want to save and load Food Vision big model. And we've done this before, so I'm going to let this keep training here. But let's write some code to get ready. So from going modular, we're adhering to our PyTorch workflow here. So create a model path. Potentially we call this one fnet b2 Food 101 model path equals 09 pre-trained fnet b2 feature extractor and Food 101 20%. Remember, our goal here is to try and beat the original Food 101 paper with 20% of the training data. And we're going to save the Food Vision big model with utils.save model. And the model is going to be fnet b2 Food 101. Of course, this is our model up here. once it's finished training. We're just preparing this code for when we know how long this first epoch is going to take. It should let us know how long subsequent epochs are going to take. The target directory will be models, and then we'll put the model name is going to be FNet B2 Food 101 model path. Wonderful. And then what do we want to do after that? Well, let's load it back in and see how it works after we've saved it, of course. So we'll create a Food 101 compatible FNet B2 instance, and then we'll go loaded FNet B2 Food 101, and this is where our function that we created before, FNet B2 transforms, create FNet B2 model, num classes equals 101. So we're just creating an instance of it there, and then we can load the saved models state dictionary, which is what we're saving with this function up here. So loaded FNet B2 Food 101, we'll go load state dict equals torch.load, and then we'll pass in the full file path here, which will be models slash this one here. And we'll just get rid of those extra apostrophes. Beautiful. So that's going to be saving and loading the model and plotting the loss curves. Oh, we're so ahead of time here. But it looks like our model might be doing a test step. Beautiful. So we're almost finished through the first epoch, because the way our train function is set up is that it goes through all of the training data loader first, and then it evaluates. So what can we do after this? While we're waiting for this first epoch to finish. You're getting experience here as a real machine learning engineer, right? Because a lot of the time you're trying to work out things to do while your model trains. So we'll check out Food Vision Big model size, but we'll save that for a second because I think, oh, there we go. Look at that. Oh my goodness, the first epoch of Food Vision Big. Have a go. Epoch number 1. The training accuracy is just under 30%, but recall this accuracy value, or these accuracy values, are across 101 classes. And then, oh my gosh, we're almost at 50% accuracy already for the first epoch. So what's our goal? 56.4% accuracy. Okay, we've got 4 more epochs to reach that. But it looks like on my end, on my P100 GPU, it's taking 264 seconds per epoch. So what is that? 264 divided by 60, what do we get? Oh, well, that's not going to work, is it? 264 divided by 60. So about 4.5, 5 minutes, give or take, per epoch. So that means this is going to take, I'm going to write a little note here. So note, depending on your hardware, running the following cell may take 15 to 20 minutes. Takes about 15 minutes, or maybe longer. If it's 5 minutes per epoch, it might take 25 minutes, or 4 minutes per epoch, or 7. It's saying it's going to take 17 minutes total, so I'm going to say 15 minutes. Takes about 17 minutes on a NVIDIA Tesla P100 GPU. So again, depending on where you're running this may take a while. But as I said before, one of the big problems in machine learning is figuring out something to do while your model trains. So I'm going to go take a little walk and stretch outside for a bit, maybe make a cup of coffee, and I'll come back once training has finished. If any errors happen, I will let you know, but I'll see you once all of these epochs have been completed. And I'm back. Look at that. Training is all done. We've got a green bar. And check out that. The test accuracy. We've trained our biggest model yet. Food Vision Big is just under 58% accuracy, which, look what we've done. We've beaten the original Food 101 paper's result of 56.4% accuracy with only 20% of the data. So that is very exciting. Why is that? Because we've just done something on my end, it took about 18 minutes. 18 minutes for training. May have taken a bit longer depending on the hardware you're using, or if your hardware is faster, that might have gone quicker. In 18 minutes, that wasn't possible 10 years ago. With free hardware and, well, I'm paying for Google Colab Pro, but it's quite cheap compared to, you get the picture. And free software. Have a look at this. When did this paper come out? Maybe in 2011? Food 101 paper. Do we have a release date up the top here? Doesn't look like we do. Let's have a look. When did the Food 101 paper come out? 2022, 2014. So just under 10 years ago, because it's 2022 as I'm recording this. But if we look in here, days, look at this. This is paid by a considerably longer training time of 6 days. So the original paper took 6 days to train on a NVIDIA Tesla K20X, whereas ours took just under 20 minutes. How cool is that? That just shows how far the field of deep learning has come. Now, like all good cooking shows, we've prepared this earlier. We've written this code before to inspect our model's loss curves. Let's check it out. Oh my goodness, they are some good looking loss curves. Even with all the extra data and extra classes, our model is still performing well. And you know what? If we kept training for longer, I think it would even improve. Those data regularization techniques that we use and model regularization, such as label smoothing and trivial augment, data augmentation, look like they're helping because our test loss is still lower than the training loss, which means our model still has more to learn or is hinting at that. Now, of course, we can save the model and load it to verify that it works. Beautiful, saved and loaded. And while our model was training, I went for a little walk, made a cup of coffee, and also wrote this code here to check the Food Vision Big model size, which is what we've done before, except with just a different path here. So let's see what the model size is. Wonderful, it's only 30 megabytes. So why is that? We've trained it with a lot more classes, but really all we've done is compared to EfficientNet B2 for Food Vision Mini, oh my goodness, we've covered a lot of ground, which was only 29.8 megabytes, we've only had a slight increase in model size. The reason is because we've only increased the number of parameters in the final layer. We've kept all of the base parameters the same. So if we get a summary of our model, let's get our FNet B2 summary, and we'll get this as well. We'll go right down to the bottom. There we go. This is for FNet B2, not FNet B2 Food 101. So that's going to be for Food Vision Mini. So we have a total parameters of 7.7 million, thereabouts. And then we can go here. This is for FNet B2 Food 101. So if we look at the total number of parameters, we don't have that large of a discrepancy here, about 100,000 more or so. So that is only changing our model size slightly. So we should get all the benefits that we've got with fast inference time for our original Food Vision model, Food Vision Mini model that is, for our Food Vision Big model. So with that being said, we've got our biggest model yet, Food Vision Big. I think let's deploy this into an app, eh? Let's replicate Food Vision Mini, our deployed app, but with our Food Vision Big model. So you might want to go ahead and give that a shot. We've already done all the steps that we need to do up here, deploying our Food Vision Mini app to Hugging Face Spaces and creating a Gradio app with it. So my tip to you would be to first create a Gradio app that works within Google Colab using Food Vision Big, and then try and deploy that app to Hugging Face Spaces. And that's what we're going to work towards in the next series of videos. I'll see you there. Welcome back. In the last video, we did the very exciting thing of doing something that wasn't possible 10 years ago. We trained our biggest model yet, Food Vision Big, which is an EfficientNet B2 feature extractor, and we beat the original Food 101's paper result of 56.4% accuracy on the test data set using only 20% of the training data. Now, of course, there's a little caveat here because we only evaluated our model on 20% of the test data. So my challenge to you would be to evaluate our trained model on 20% of the training data on the whole test data set and see if this result holds water. How cool is that? So their model took 6 days to train, whereas ours is under 20 minutes or thereabouts. I'm continually blown away by this. And the loss curves looked amazing. If we trained our model for longer, perhaps it would perform better. But let's not stop there. We deployed our Food Vision Mini app, and we want to do the same thing with Food Vision Big. So let's go turning our Food Vision Big model into a deployable app. Let's call it that, deployable app. So why do we want to do this? Why deploy a model? As we've said, deploying a model allows you to see how your model goes in the real world. The ultimate test set. So of course, when you deploy a model, you're going to find out things or find out bugs that you didn't know were going to happen. That's inevitable. So that's why we do it. So how do we do it? Well, with the Food Vision Mini, I'm getting all these names confused. We've built so many projects now. Food Vision Mini, we started off by creating an app structure. So we're going to replicate something very similar to this, but for Food Vision Big. So let's go down into here and we'll create an outline. Let's create an outline for our Food Vision Big app. So what do we want it to look like? Well, of course, here's something I prepared earlier. If we scroll down, this is section 11, turning our Food Vision Big model into a deployable app. We want to create the following file structure. We've already got a demos directory. Then we're going to create Food Vision Big, and within it is going to be a few of these files. Now, this is just like Food Vision Mini. We've got our pre-trained model. We've got our app.py. This one is a little bit different, classnames.txt. We haven't done that before, but because we're working with 101 different classes, rather than save all the class names in app.py, we'll just save them to a text file and load them in programmatically. We'll create an examples directory so people can test out our model. And then we'll have our model.py file, which will define the architecture of our model. We've already got the function for that, create fnet b2 model. And then of course, a requirements.txt file to tell Hugging Face Spaces what dependencies our app needs. So let's go and copy this and we'll bring it into Google Colab. This is what we're going to start working towards making. So how about we start off making the directory? Of course, we want to do as many things programmatically as possible. So from pathlib import path, and let's go create Food Vision Big demo path. So we'll go Food Vision Big demo path equals path demos Food Vision Big. And we want to deploy our well-performing models as soon as possible because of course deployment is as important as training. So let's make Food Vision Big directory. Food Vision Big demo path.mkdir for make directory. We'll make the parents, if they don't exist, the parent directories that is, exist okay. We'll also set that to true so it doesn't error if the file already exists. And then we're also going to make Food Vision Big demo examples directory while we're here. So let's go Food Vision Mini or Food Vision Big. I've got Food Vision Mini on my mind because we've worked on it so much. But now we're on to Food Vision Big / examples.mkdir. So this is just making an examples directory. Parents equals true, exist okay equals true as well. Let's see what happens when we do this. And then if we go ls demos Food Vision Big, what do we get? All it has is an examples directory. So this is our demos file, Food Vision Big, and then examples. So beautiful. By the end of this couple of section of videos, section 11, we're going to have a file structure like this so that we can deploy Food Vision Big to Hugging Face Spaces. So if you want to continue on, my challenge to you is to put an example or two in the examples directory. You know what I'm going to use? I've decided I'm going to use the images, the one we've been using for the whole course, pizzadad.jpg. I'm going to download that and put it in the examples directory, that's going to be our Food Vision Big examples image. So give that a shot, and we'll do that in the next video. I'll see you there. Welcome back. We're moving towards filling out our Food Vision Big demo directory, so we have an app we can deploy to Hugging Face Spaces. And now we're up to putting an example in the examples directory, because after all, that's what a demo is about, right? Showing off what our model can do. So let's go downloading an example image and moving it to the examples directory. So of course, you could put any image you want into this examples directory. You could randomly select images from the Food 101 data set. You could put your own images in there. Just, I would suggest that they have the same, or it has the same classes as Food 101 class name. So you can demonstrate, or you might want to demonstrate where the model doesn't work. And we'll talk about that later on. So yeah, something like this. You may have a photo of ice cream, or some grilled salmon that you've cooked, or maybe some garlic bread. Your favorite food, you could put it in here, but I'm going to put in Pizza Dad because, well, we've been using that the whole course. So I'm going to copy the raw link here, the download button, by going PyTorch images Pizza Dad. So if we come back into here, I'm going to first download and move example image. So I can download it with wget, and then I can move. That's going to download a file called 04 Pizza Dad, which has come with us all the way from section 4. And then demos, I'm going to move it into Food Vision Big / examples / 04 Pizza Dad.jpg, and we'll see how that goes. Shouldn't take too long. Beautiful. There we go. Let's just make sure it's in the examples directory. Wonderful. That's exactly what we want. And now we can move our model. How about we move our model from here? We have a big model here, Food 101 20%. We can move that into Food Vision Big as well. We could drag and drop it from Colab, but I might just go MV models 09. I might copy this path here actually, rather than type it all out. Content, I'm going to get rid of that. And then where do we want to move it to? Well, of course, we want to move it to demos, Food Vision Big. And we'll see how that goes. So it should move from here into here, Food Vision Big. There we go. Wonderful. Now, of course, if we try to run this again, it's going to error. Well, you wrote some code before in the Food Vision Mini section to make sure that this doesn't error, but this is all right for now. We just run it once and it moves in here and it lives there now. So we've moved our example and we've moved our model. What else do we have to do? Well, we have to create a classnames.txt file. We haven't seen that before. So let's do that in the next video. You might want to give it a shot. What we're going to do is turn this list into a txt file. So just a plain text file with one food per line in the text file. So give that a shot of writing that to file, and we should have Food 101 classnames.txt in Food Vision Big. I'll see you in the next video. Welcome back. In the last video, we filled out or started to fill out our Food Vision Big demo folder with an example image and our pre-trained model. So let's not stop there. Let's create a list or a text file with all of the class names. So why are we doing this? Well, we don't necessarily have to. We could just import this list straight into app.py, which is similar to what we did for our Food Vision Mini. So I'm just going to write this down. I want to go class names. You might have already done this, classnames.txt. So I'll write, let's save all of the Food 101 class names to a .txt file so we can import them and use them in our app. So if we go back up to what we did for Food Vision Mini for app.py, we just set up the class names within app.py as a list. But because we have 101 different class names, that might be a bit cumbersome to have a list with 101 different objects within this file. So this is just out of not necessity, but rather neatness. So let's check out the first 10 Food 101 class names. And of course, Python is quite quick at reading text files, so it won't really have any performance issues with our app. So there we go, the first 10. So how can we save this to a text file where we want our text file to have one line per class name? So I reckon we can give it a shot by first we'll create a path. So create path to Food 101 class names. And then we want to go Food Vision Big, and then class names path equals Food Vision Big demo path / class names. We'll keep it nice and simple. We could do it Food 101 class names.txt, but that'll do. And then I'll just get this. We'll check out that. Beautiful. So this is where we want save our class names. We want a text file with all of these in it over here. Now let's go write Food 101 or class names to text file. So we can go with open. We're going to open Food Vision Big. I think I've still got it in the clipboard. Yeah, we're going to open this path as a write. So we want to use the write permission for W for write, as F for alias for file. And then I'm going to print here a little info tag, info, saving Food 101 class names to just this file name. Beautiful. And then we can go f.write, so file.write, and then I'm going to use a new line. So a new line, so we want to go apple pie, new line, baby back ribs, new line, baklava. We'll see what this looks like in a second. Then I'm going to use the join string method, and then it's going to join everything in Food 101 class names. And hopefully this looks like what we want. New line per class name. That's the new line Python string symbol, by the way. Let's run that. Beautiful. Let's see how this looks. There we go. There's our class names.txt. Exactly what we wanted. Wonderful. So this is just a simple file that we can now import into our app.py later on. So let's actually try that out to see how it works. Open Food 101, class names file, and read each line into a list. So what we just did was we saved them to a text file. Now we want to do the reverse. See if we can read the text file back into a list like this. So how about we go with open, and we want to open our Food Vision Big class names path, but this time we'll have a different permission. This is going to be the permission as R for read. We'll still read it in as F, short for file, and then we'll go Food 101 class names loaded. So this is similar name to this list, but this is the original list. We're just creating this loaded version to know that this is the one that we've loaded in. And we're going to use a list comprehension here. We'll use food.strip. So .strip, what does it do? Let's look it up. Python strip. So remove spaces at the beginning and at the end of each string. Now, why do we want to do this? Well, because if we go back here, we've got class names.txt. If we read this in, this is actually, new line is equivalent of having like space afterwards. So how about we just do it without strip first and see what it looks like. So food for food in f.read lines. And so read lines is Python read lines. What does it do? Return all lines in the file as a list where each line is an item in the list object. Beautiful. That's exactly what we want. So we'll go back to here. Let's see what this looks like, hey? Food 101, class names loaded. Yeah. So this is what I meant by, if we read this in line by line, because we've got new lines between each of these, it comes in like this, /n, which stands for new line, which is sort of like a space. So that's why we call .strip here, and then we read it in. Beautiful. So now we've got a way to go from our class names, which of course we got this from our PyTorch Vision dataset. And then we save it to a text file here. And now we can read it back in as a list with the code here. So that's what we'll be doing in our app.py when we do that. But before we get to app.py, our next step is to, what do we need now? So we've done this, we've done examples, we've done our model. Let's do model.py, or sorry, our saved model that is. Let's do model.py, hey? And we've already done this in Food Vision Mini. So you might want to jump ahead and give it a shot yourself. Otherwise, let's do it together in the next video. I'll see you there. Welcome back. In the last video, we saved our Food 101 class names to a text file, and then we also wrote some code to read them back into a list. So now let's keep working towards making the required files for our Food Vision Big demo. We're up to 11.3, which is turning our Food Vision Big model into a Python script. In other words, model.py, which we have subsequently done before with Food Vision Mini. So if we were to scroll back up to Food Vision Mini, we created model.py up here. You know what we can do? We're going to cheat a little and copy this whole file, because we used the same model for Food Vision Mini as we did for Food Vision Big. The only thing we did for Food Vision Big was adjust the number of classes. And of course, our create fnet b2 model function is flexible enough that we can just do that on the fly. So let's bring this down to here. The only thing we have to change for this cell is, instead of Food Vision Mini, we want to do Food Vision Big. So if we run that, what do we get? Let's check our file system. Food Vision Big, model.py. There we go. Wonderful. So that is done. The next step is to create a Gradio app, 11.4. Now, of course, we've already done this with Food Vision Mini, app.py. So that's my challenge to you, is turning our Food Vision Mini or Food Vision Big Gradio app into a Python script. So we're going to skip the creating of the demo app in Google Colab. You're more than welcome to try that out. But we're going to create app.py straight away because we've had some practice already, and that way we're one step closer to deploying our model on Hugging Face spaces. So give that a shot. You might want to reference this section up here, app.py for Food Vision Mini, but remember, you're going to have to change a few little details so that it works for Food Vision Big. Let's do that in the next video. Welcome back. In the last video, we created a model.py script for our Food Vision Big demo, and we are getting one step closer to turning our Food Vision Big Gradio app into a Python script. So let's take that step in this video, hey? And my challenge to you was to reference this one and give it a shot creating app.py for Food Vision Big. You might have already done this, so if you have, well done. Otherwise, let's do it together in this video. So the app.py script is going to be largely the same, except there's going to be a little bit of a difference here. So for class names, we'll need to import from classnames.txt, the text file that we saved before, rather than with a Python list. So model and transforms preparation, we'll need to make sure our model is suitable for Food Vision Big. Predict function, this can stay the same as the original predict function that we created way back when. And finally, the Gradio app interface, this will change slightly from Food Vision Mini to reflect the Food Vision Big updates. Of course, because we've got Food Vision Mini, it's got some description about what Food Vision Mini does. We're going to have to change that to Food Vision Big. So let's get started, hey? Number one, we need to imports and class names setup. So let's start by importing Gradio as GR. Now, of course, We don't have to rewrite this in our notebook, but the goal of this cell is, I'm just going to put this magic up here. We want to write file to demos food vision big /app.py. This script is not going to run in our notebook. This script is going to run on Hugging Face Spaces. So we need to make sure Hugging Face Spaces knows all of the imports we need. And this will go for almost any place you decide to deploy your app. You will need to define what requirements and dependencies it needs. So import torch, and then we're going to from model, which will be model.py. We're going to import, I'm just going to comment this out so we get some code formatting. We want to import create fnet b2 model. That's going to create our feature extractor. Import create fnet b2 model, and then we're going to go from timeit import default timer as timer. We'll need this for our predict function, and then of course from typing import tuple and dict. So that'll be for our predict function as well. So now here's where one of the major differences is going to be. This is setting up the class names. So we're going to go with open. Now we have to reference the classnames.txt file here. So because of course app.py is going to live within Food Vision Big. So we want to read in classnames.txt with R as the permission for read as F. And then we can do our little list comprehension trick that we did up here, which is, oh, excuse me. Here we go. This is what we want. Something like this. So let's bring it down here. Do we have what we need? Maybe we'll just call it class names. Class names equals food.strip for food name. Let's go food name, just to confuse ourselves a little bit. Food name dot strip for food name in f.read lines. Wonderful. And now we can go to is model and transforms preparation. Preparation. Is that how you spell preparation? Doesn't really matter. That'll do for now. So what do we need to do here? Well, we've got our create model function here. And that is, of course, going to return back the transforms as well. So let's start by create model and transforms. So we'll go fnet b2, and we'll go fnet b2 transforms. We can call it just fnet b2 here rather than fnet b2 101, because this app.py is going to run in an isolated environment. So separate from our Food Vision Mini and separate from the rest of our notebook. So I'm just going to call it fnet b2 and fnet b2 transforms, and we can create that by going create fnet b2 model, and then we'll pass in here num classes equals 101. Of course, we could also use the length of our class names variable, which we created above. I'm just going to stick with 101. We'll hard code that. Beautiful. And so what do we want to do next? Well, we need to load the saved weights. How can we do that? Well, just like we've done before. fnet b2 dot load state dictionary, which is what we've saved. And then we want to go torch.load, and our file is equal to, it's going to be this path name here, because this app.py again is going to live within Food Vision Big. So we want to load it from this path. But we can remove all of the things at the front because it's going to be in the same file level as app.py. And then we can also hard code it here. Map location equals, I've been burned by this before, trying to load a model that was trained on the GPU. So when PyTorch saves it, it's going to recognize that this was trained on the GPU. So when I try to load it back in, I'm going to try to load it back onto the GPU. And if we don't map it to the CPU manually, we might get an error there. So of course, if you had access to a GPU, you could put device agnostic code here. But because we're going on Hugging Face Spaces, the free tier offers a CPU. So we're going to load it to the CPU. So I'm just going to write this in here, load to CPU. Beautiful. What are we up to now? Number 3 is predict function. Now, this is going to be quite an easy one because we've prepared this one earlier. So let's go back to this is going to be no different to our app.py script for Food Vision Mini. This is just the same predict function we wrote way back when. Where do we make it? Creating a function up here. Yeah, there we go. Creating a function to map our inputs and outputs. The same function here, we're going to copy it into our Food Vision Big script. Food Vision Big. Wonderful. So remember, the whole premise of a Gradio demo is to have inputs, some sort of function, outputs. And that's our function to map the inputs to the outputs. So finally, number 4 is we need what? We need a Gradio app. And so what can we do for this one? Well, this is again going to be the same as our Food Vision Mini. If we go to app.py, but of course we're going to customize it for our, and we learned as well, if we're deploying to Hugging Face Spaces, we don't need the share parameter in launch. But let's go back. So all I've done is I've just copied app.py, the Gradio part, into here. But now let's change this to Food Vision Big. And then I'm going to put an emoji here. Command Control Space on my Mac. It might be slightly different for yours. And I'm going to go eyeball for vision, and then food, and then a muscle for big. Or actually, maybe it should be food first. Food Vision Big. Beautiful. So this is still correct. An efficient net B2 feature extractor. Computer vision model to classify 101 classes of food from the Food 101 dataset. And here's something I prepared earlier from the PyTorch deep learning repo. I've got in here extras, all the class names for Food 101. So in a text file, nice and simple to read, I'm going to link this in here to classify 101 classes of food from the Food 101 dataset. I'm just going to link this in here, so that way if someone wants to know what classes it can do, we can put that in there. And then where was it made? Well, this is going to be slightly different. I'm just going to put this link. So where are we at? Food Vision Big. There we go. So this is just section 11. Been good to reference these things, you know, so people can find out how to do it themselves. And so what do we need to do? Is this correct? Examples list is going to be correct, of course, because we have the same examples directory layout as our Food Vision Mini app. So this is just going to read in examples plus example for example in OS lister examples. So our one example for this case is going to be the classic pizza dad image. And I think that is enough. Do we have to change anything here? Well, I think we're going to find out once we deploy this app, right? We could change this to number of top classes. How about we change this to 5? Because instead of 3 classes, we now have 5 potential candidates. So with that being said, I think we write this to file and move on to the next and final file that we need for Food Vision Big. There we go. There's app.py. The final one that we need is requirements.txt. So give that a shot. Reference the requirements.txt file that we made up here, and we'll do it together in the next video. We'll complete the file structure for Food Vision Big. I'll see you there. Welcome back. In the last video, we created our Food Vision Big app.py script, which is what is going to be the brains behind our Food Vision Mini or Food Vision Big demo on Hugging Face Spaces. But now let's finish off the Food Vision Big file structure. We need a file requirements.txt, and in fact, our Food Vision Big model has the exact same requirements.txt as our Food Vision Mini. So, because all we've done is we've just scaled it up. So let's write file demos/foodvisionbig/requirements.txt, and then we're just going to put that in there, and then we're done. So our Food Vision Big directory structure is complete. So what do we do now? Well, let's zip it up and download it, hey? 11.6, I believe we're up to. So downloading, or maybe we'll put a little title in here. So we'll keep things neat. 11.5, we wanted to creating a requirements file for Food Vision Big, and this is, of course, requirements.txt. Lovely. So let's now downloading our Food Vision Big app files. And once again, we have done this before. So we're going to reference our previously written code for Food Vision Mini. Here we go. So first and foremost, what we did is we changed into the Food Vision Mini directory and then zipped it from the inside, ignoring some files here. So let's do that. And then of course, we downloaded it using this code. So we'll come back and get that in a second. Let's first zip. We'll change this to Food Vision Big. We'll do a little trick here. Can we get multiple cursors? I'm holding down Option on my Mac. There we go, which might be Alt on another keyboard. So Food Vision Big, Food Vision Big.zip, Food Vision Big. Everything's looking big. Let's see what we get. There we go. That's what we want. Food Vision Big.zip. Now, of course, we can download this by manually clicking here, or we could do it programmatically by going up back to here, downloading our Food Vision Mini app files. Let's copy this. We'll bring it down here. So this is just going to try and download it. If it's in Google Colab, this will work. But if you're running on a local machine or something like that, you may have to just download this manually or access it however you can. So let's change this to Big. And we'll change this one to Big as well. And we'll run this and we'll download our file. There we go. Downloading foodvision_big.zip. And hey, we'll wait for this to download, but we've also gone through the steps to deploy this to Hugging Face Spaces. So my challenge to you is to go back to these steps here, uploading our Food Vision Mini Gradio demo to Hugging Face Spaces, and see if you can go back through them again and upload it and get a running demo of Food Vision Big. Of course, you can reference the notebook here. We've got the steps there, but that's what we're going to do in the next video. We're going to finish off Milestone Project 3 by deploying our app to Hugging Face Spaces and having a live demo of Food Vision Big. So give that a shot, and I'll see you in the next video. Welcome back. In the last video, we downloaded foodvisionbig.zip, and I'll just show you here. I also issued you the challenge of giving it a shot to deploy it to Hugging Face Spaces. So potentially you've already done that, and if so, well done. If not, let's now do it together, hey? And we've got downloading our Food Vision Big app files. We zip them together, and then this cell ran. It took a couple of minutes on my Google Colab instance, or maybe not even that, maybe a minute or so. But of course, you can also download it manually here. And then finally, if you want to reference it later on, I've got these files on the course GitHub. There's foodvisionbig.zip, foodvisionmini.zip, and a little table explaining what they do. So let's now, if you wanted to deploy this to Hugging Face Spaces, for Food Vision Mini, we went through a series of steps. And in fact, these are the exact same steps that we did for Food Vision Mini, except replaced with Food Vision Big. But if you want to see different ways to upload to Hugging Face Spaces, you can go to this link here, getting started with repositories. There's adding files to a repository via the web UI. And this is what we did last time, adding files to a repository via terminal. So if I go into my terminal, we use something like this. Yeah, Food Vision Mini video. For a change of pace, let's add files to a repository via the web UI. And finally, there's one more that's not quite listed here just yet. That is, I've listed that here, is using the Hugging Face Hub client library. So that's a third option. Of course, all of these are linked in the course book. So I'm just going to put this here, this link in here. Let's go section 11.7. Let's bring Food Vision Big to life. And I'm going to write here, deploying our Food Vision Big model app to Hugging Face Spaces. This is so exciting. Our biggest model yet in a deployed app demo. And let's bring Food Vision Big, I keep saying mini, to life by deploying it to the world. See steps here. Wonderful. Just going to turn that into Markdown. Okay, so we've got foodvisionbig.zip, and we've got an option of uploading with the Hugging Face Hub library. We've also got the option of uploading through the web UI, which is what we're going to do in this video. And then we've also got terminal. So a bunch of different ways here. We're just trying to explore a few so we can get a bit of practice. And this is Food Vision Mini video. So let's now go to huggingface.co, and we can create, once you've got an account, you can create a new space by going to here. Then we've got create a new space. So this is my account name. I'm going to call my new space Food Vision Big. You can call yours whatever you want. I'm calling mine Food Vision Big Video, so that you know that I've created this during the video recording. But on the demos file, you'll be able to see the live demo of Food Vision Big at mrdburke/foodvisionbig. So there's Food Vision Big's already running. That's a little spoiler, but as I've been saying, this is a machine learning cooking show. So we'll come back to creating a new space. Remember here, new space, Food Vision Big Video. I'm going to use MIT license. You can choose your own license. Gradio, which is our SDK. Public. Let's create a new space. Now, for Food Vision Mini, we cloned this repo locally and then uploaded some files using Git and Git LFS. But for now, let's just see how you can add files manually. And what we might do is change the README first. So what I'd like to do is also change the emoji. Let's change this to, maybe we go food. What can we do for here? Let's do a taco. Beautiful. Food Vision Big Video. That'll do for now. Commit changes. And so what files do we want to upload to here? Well, we want the files that we created from Food Vision Big. And I've got these downloaded locally, Food Vision Big zip, so I'm going to open that up. And here we go, here's my downloads. Food Vision Big, requirements.txt, app.py, model.py, class names.txt, examples. We want all of these on the Hugging Face Hub. So let's see how we can do that. We might come over here, and then I'm going to go add file, or upload file, sorry. And then we can just drag this to here. I'm going to commit the changes. That'll be pretty quick to upload. I'll go back. As you see here, it's no application file. This is going to look for an app.py file. We might just upload that one now, and it'll start building it. But of course, it's going to error because not every file is available. So there we go. We get a building status light. And if we look at the logs, it's going to start trying to build. Maybe that was a bit too quick. We'll just let that run in the background. But of course, it's going to error because it doesn't have access to things like the model file. We'll put that up there. Commit changes. And as you're seeing, this is a pretty manual process. So the reason why we did it code-based in for Food Vision Mini is just to show you how if you're working on a larger project and you had a lot more files and you were doing a lot more changes, dragging and dropping is probably not sustainable over the long term, but it's definitely one option. So let's go to here, classnames.txt. We'll upload that. What else do we need? We need our model file. Upload that. Now you'll see this is going, because it's a larger file, 31.8 megabytes on my Mac here. It's going to take a little while, a minute or so to upload and process, because behind the scenes, Hugging Face is using Git LFS, which stands for Git LFS, Git Large File Storage, to process and track that file. So that's what it's doing behind the scenes, and we'll just see that uploading. I'm just going to pause the video here for a minute and come back once this is finished, and if it errors, I'll let you know. There we go. So we've got our uploaded model file here, and as you can see, this file is stored with Git LFS. We can't display it. That's what the Hugging Face space is saying, but we can still download it if we want. So there we go, 31.8 megabytes, which is the same as this. So let's go back, and we might, yeah, there we go, a runtime error, which is expected, right? If we look at the logs, what do we get? Maybe we need a full screen here. Oh, we're not getting any logs. but we kind of expected that runtime error to happen because our app.py file was uploaded and it tried to build the app without access to the other files that it depends on. Now, we're missing one more file here. This is a little bit tricky because examples is a directory with a file inside it. And as of now, the time I'm recording this video, if I try to upload a file, I can't actually upload a directory. So if I try to upload this, I can't do it. You might find a way and it may update in the future, but I'll show you my trick to creating a directory in the UI. So if I go create new file, and then I go examples / demo file delete later.txt and go demo to delete. This is a little trick to create this file, demo file delete later.txt, in the examples directory. So if we watch this, now we have an examples directory here, right? Examples. But we don't want this file in here. So before I delete that though, I'm going to upload another file to /examples. And the file I'm going to upload is, of course, the Pizza Dad image. I could upload it from here, but I've also got Food Vision Big examples. This one, it's the same image, but just for completeness, I'll upload it from the Food Vision Big directory. And that was what we created in here. Food Vision Big examples. So it's going to take a little bit to upload because it's an image, a little bit larger of a file compared to just a text file. And then we can come back to examples and delete this txt file. A little bit of a hack, but that's just showing you how you can upload a folder through the UI here. Now, of course, we could do this all programmatically, which is what we did for Food Vision Mini. But now you'll see because we've made a change, our app is going to be building. There we go. Do we have any errors? Oh no. Default theme. What have we got wrong? Bytes.io object. So maybe our image is not working. We run this. Building. App.py. All right. So I'm going to figure out what's going wrong and we'll discuss it in the next video. Or I'll pause this video, figure out what's going wrong, and I'll let you know the fix. Now, it turns out there actually was no error. We've got running. Food Vision Big is officially live. What I did do though is I went into settings and then I clicked factory reboot this space, and all it needed was just a restart to kick things off. So it turns out our little trick to upload a file here worked, and we've got Food Vision Big is officially deployed. It's so exciting. So let's now try it out, make sure that it works. I haven't tried this out. This is the first time I tried it. It does work. Pizza. Beautiful. And now let's try it officially by, I've got something I prepared here earlier with Stable Diffusion demo. Of course, this is running on Hugging Face Spaces as well. So this is BeigeNet. Maybe I'm saying that incorrectly, but this is that one we looked up before. So let's try to see if Food Vision Big, I'll click on this image here. This is a generated image. So I'm going to save this as BeigeNet and see if Food Vision Big can classify this correctly. Let's go back to our model, clear, and then, oh, where'd my downloads go? I want to upload from downloads, BeigeNets. This is that image I just downloaded. Let's see how the model goes. Food Vision Big. It works on Pizza Dad. BeigeNets, beautiful. I didn't even know what that food was before we built Food Vision Big. So that is Food Vision Big deployed. And of course, I'm going to link this into here. Let's go see our deployed app here. Now, I'd love for you to try it out on your own images of food, and please share them with me on the Discord and the course GitHub discussions page. If you expand upon this app, I'd love to see that as well. How could you do so? Well, Gradio has some great features. Gradio.app. You can go into the docs, and Blocks is a new API in Gradio that you can create some more advanced style apps. So some things you might want to try is maybe even adding another food class that isn't in the Food 101 dataset. You could add 50 or so images you have of that food to here. And then another one would be is a big problem with our app actually is what happens if you upload an image of not food to our model? What's going to happen? This is an image of a Cybertruck from Tesla. What's our model going to predict? Ice cream. Maybe that's an extension for our Food Vision Big model or any other type of deployed model. And of course, that's going to be in the exercises. This is one of the places or one of the reasons why we deploy our models so that we can find potential failure points of our deployed Food Vision models. So with that being said, that's the end of Food Vision Big. Congratulations on deploying 2 machine learning apps in the one section. Let's finish this off with some main takeaways. I'll see you there. Welcome back. You should be super proud of yourself for making it all this way. We've come a long way. Let's try it out, our Food Vision Big deployed machine learning model to the internet. Anyone can use this link. Be sure to share it with your friends, and I'd love to see yours. 2 thumbs up for finishing Food Vision Big. And yeah, we've come a long way from right back in the fundamentals, or even the workflow. Was it fundamentals? We predicted a straight line with PyTorch, somewhere in here. And now we're deploying computer vision models to the internet for everyone to use. So congratulations on making it to the end of Milestone Project 3, but here are some main takeaways. And the first one is deployment is as important as training. So once you've got your first working model or a good working model, your first question after that should be, how can I deploy this and make it accessible to others? So building on the back of PyTorch transfer learning, one of the main takeaways there was, is there a pre-trained model for the problem I'm working on? And Hugging Face is a great place to find pre-trained models. The same thing with Torch Vision.models or other PyTorch domain libraries. So when you're working on a problem, ask the question, is there a pre-trained model for my particular problem? And then the next question, after you've got a pretty good model, how can I deploy it and make it accessible to others? The reason being is because deployment allows you to test your model in the real world rather than on private training and test sets. Then, of course, for machine learning model deployment, the 3 important questions, of course, there's many more, but these are just 3 big questions. What's the most ideal use case for the model? How well and how fast does it perform? Once you've thought of the most ideal use case, you can start there and work backwards. So for Food Vision Big and Food Vision Mini, we found that, hey, we want this to work on a mobile device and we want it to be fast. And we want the predictions to come back online. We want it to happen in real time. But there's a few different options here, such as on device or also known as the edge, the cloud being another computer that isn't the actual device that someone is using. And these can mix and match with online prediction, real time, and offline prediction, batch. So let's go back. Deployment options are aplenty. We've seen Hugging Face Spaces, which is one of the best ways to get started. The same thing with Gradio. And in fact, Hugging Face Spaces is a great place to host your machine learning portfolio. So you can create a whole bunch of machine learning demos and show off your machine learning skills, which is what we've got here already. Mr. D. Burke, these are mine. Food Vision Big video, Food Vision Mini video. They're the 2 ones we did together. And these are ones I prepared earlier, but you could start to build this out. In fact, if you do, please share them with me. I'd love to try them. Never stop experimenting. So even through Milestone Project 3, we did a bunch of experiments. We tried 2 different models, EfficientNet B2 and a VIT feature extractor. And we even experimented with the Food 101 dataset to use 20% of the data. So your next experiment could be with Food 101 to use more images. So what have we got? We did 20% here. So an extension could be to use all of the images and see how much better the model's results go. What did we end up with? About 57, 58% accuracy, thereabouts. So see what happens if you added in the rest of the data. Just beware, it may take a little bit longer to train because there's 5 times as much data. And then finally, what's our last main takeaway? There's a fair few here. We've covered a lot of ground. And machine learning model deployment is part of the engineering practice of ML Ops, which stands for Machine Learning Operations. And so machine learning operations is an extension of DevOps, which is the practice of development operations, and involves all the engineering parts around training a model, such as data collection and storage, processing, model deployment, model monitoring, versioning, and more. We haven't covered all of those things, but the good news is we've had hands-on practice of deploying a model to the real world, something that someone else can use. So if you'd like to read more about this, because it is a rapidly evolving field, I've linked a bunch of things in the PyTorch extra resources section, which is available in the book version of the course. We have resources for machine learning and deep learning, some great books here, but there's a whole bunch more here. PyTorch Pure resources, libraries that make PyTorch better, books for PyTorch, where to find data sets, tools for deep learning domains, computer vision, NLP, speech and audio, recommendation engines, time series, and finally, how to get a job as a machine learning engineer. To finish off, there are some exercises. I've created a template notebook. I've created a solutions notebook. They are here. And there's a video, a live walkthrough of the solutions on YouTube if you'd like to watch me going through the exercise template there. And then finally, if you'd like to learn more about some of the topics that we've covered in here, there is a bunch of extracurriculum resources there. One of my favorite recent articles that I've read is Moving ML Inference from the Cloud to the Edge. So I'd highly recommend going and check out not only that, but everything that's here. If it's made it here, it's a good resource. But that's all from me. Thank you so much for following along with Milestone Project 3. We've now officially deployed our Food Vision Mini model to the internet as a usable app, and not only Food Vision Mini, but Food Vision Big. So happy machine learning, and I'll see you next time.
Hey there. I wanted to take a second at the end of it all, at the end of your learning journey, to just say this one thing. And that is, thank you. I know your time is valuable. We have limited time on this earth, and you decided to spend your time and your money, frankly, with us, doing something that takes a long time to learn. So truly, from the bottom of our hearts, I know it sounds cheesy, but thank you for dedicating your time and effort to this course. I hope you got what you wanted out of it. And congratulate yourself for getting this far, because a lot of people start, a lot of people have hopes of learning, but they give up along the way. But you didn't do that. You worked through the challenges, the problems, and you got here. Now, your learning journey doesn't end here. It keeps going. But I hope this created a foundation for you to go off and learn things on your own, get a promotion, get hired, start a new business. Whatever it may be, again, thank you and best of luck with your learning journey. This is just the beginning of whatever you decide to do in the future. So thank you and good luck.